So let me introduce today's speaker, Professor Ramaswamy Murugan. Professor Ramaswamy Murugan is a professor of physics at the Pondicherry University, India, since September 2010. Earlier, he worked as a director, Department of Science, Technology and Environment, for the government of Puducherry, India. Also, he was a visiting scientist at the University of Texas at Austin, USA, and Nagoya University, Japan, as a guest researcher at the University of Kiel, Germany, and also as a postdoctoral fellow at NTHU, Taiwan. His research focuses on the design, synthesis, and characterization of functional materials, particularly for practical applications in lithium metal batteries. His major contribution is the invention of garnet structured solid electrolyte, US patent, as electrolyte for all solid state lithium battery. Currently, he is serving as editorial board member of journal Ionics published by Springer. Also, co-editor of journal Current Smart Materials published by Bentham Science. And also, he acts as the president of Energy Science Society of India, ESSI. He is being honored as Fellow of Royal Society of Chemistry, FRSC, Fellow of Academy of Sciences, Chennai, FASCH, Member of American Chemical Society, ASCS, and Research Award by UGC India. Talking about his academic and professional achievements, he was awarded for his PhD, Physics, Molecular Spectroscopy from Pondicherry University, India. His MPhil in Physics, Condensed Matter Physics, Pondicherry University, India. And his MSc Physics, Electronics from University of Madras, India, and BSc Physics from the University of Madras, India. He has nearly 14 research fellowships like Visiting Scholar, Visiting Scientist, CSIR, Senior Research Fellowship, and so many are. Nearly 14 research fellowships. He held several administrative positions, so many around, more than 50, like some of them like Director, Department of Science and Technology and Environment, Chairman, PG Board of Studies, Physics, Pondicherry University. So he held around 18 administrative positions. Example I've mentioned, a few mentioned. He has 3 international patents and his research projects got awarded too. Coming to his publication accomplishments, Dr. Ramaswamy Murugan has 109 research journal publications, and out of which 33 are solely published on energy storage systems. Dr. Ramaswamy also published a book on solid electrolytes for advanced applications. So now, here we are going to listen from Dr. Ramaswamy Murugan about the theme for today's session. I hope you pay attention to his lecture. And so, sir, now I invite you to speak and deliver your valuable contribution on this session for today. Thank you.
Thank you, Madam Sudhati and Dr. Aripasad for providing this opportunity. Is it audible?
Yes, sir, it is audible.
Okay. So I don't know much about the background about the audience. Dr. Aripasad, can you tell me what about the audience background? So it's easy for me to cover whether I can go in advanced topics or I can focus on the basics where I can focus. So can you give some brief introduction about the background about the participants?
Sure, sir. Most of the participants will be throughout India. Various some people are from IITs, NITs, and central universities. Faculty members are there, assistant, associate, few members, and a few are student research scholars from IIC Bangalore, like that students also there, and some private engineering colleges, faculties, and research scholars. Uh, like that, 200 participants are originally. So now it is joined around 100 people. So it will increase after section once started.
Okay, thank you very much for at least I can get some ideas. So based on that, I can focus on the where I can read. Second is the I hope yesterday by both Satya and other people might have given a lot of introduction on the energy storage device, particularly on batteries. So I wish to focus very small amount on basics of the conventional lithium-ion batteries, and I wish to focus on the lithium metal batteries. Why it is so important? Why a lot of research activities on lithium metal batteries? Then I wish to focus on our contributions, particularly from the point of view of solid electrolyte for lithium metal batteries. And finally, I wish to conclude what is our present status, what type of work we are doing it, and even I can point out what is around the world, lot of what is the research status on the solid state batteries. So with this small introduction, I wish to start my lecture. If you look into this evolution of energy storage, it's not new to the world, almost 2 centuries. So from 1859 to present day, lead acid batteries in 1859 and alkaline batteries came into the picture 1950. Then lithium-ion battery 1991. So we're living quite a long time with the present technology. Slowly, people started to work on new chemistries and new technology with lithium batteries. We feel that this lithium metal battery is the future, particularly for e-mobility, even for grid energy storage. So people are really working towards what type of requirements to fulfill the future batteries. A lot of focus on the energy as well as the capacity of the batteries, particularly for EV applications. They wish to make a battery a 300 miles range for single charge. And which means that they have to think about the enhancement in gravimetric as well as the volumetric energy density. And again, this fast charging, ability to recharge batteries up to 80% capacity in just 15 minutes because they don't want to wait for quite long time to charge overnight. And lifetime also, battery lifetime, they want to propose more than 10 years and more than 150k miles for EV. And above all, safety is a very interesting, important factors for EV applications. So non-combustible, solid state separator, people think that they can ensure the safety of the battery is concerned. But if you want to bring into this market, the most important factor is the cost. The people are working very hard how to reduce the cost, but particularly reducing manufacturing cost by improving the technology. That's the requirements, and people are working hard to fulfill the requirements to provide an energy storage device for the present day or future battery. I mean, the application point of this kind. Okay, now to look at it because I'm going to talk about the future. Maybe not in the long term, maybe intermediate state. Is it lithium metal battery is the future? People are betting on lithium metal batteries due to various reasons. If you look into the specific capacity of this present day, lithium titanates, graphite, nickel sulfide, potassiums, and up to these ones, still lithium is the highest specific capacity, 3861 milliampere hour gram. Then silicon, then germanium is reasonable, sodiums, and you can see so many competitors. If you look into this atomic weight size, say the proton is the least one, the next comes lithium. Maximum voltage is concerned, lithium is 4.5 volts, and proton is just 1.5 volts. Cost also, lithium, people are thinking that its cost is very high, but I feel amount of lithium you are going to use it in a single cell is very less compared to the remaining materials are concerned. which means out of all the combinations, still lithium leads the frontier in all the aspects. Energy density, if you really think about the energy density, the best option available at present is the lithium metal battery. Almost 10 times when compared to the present graphite is concerned. So let us look back into the present lithium ion battery. So it's not a new to the world. The concept has been introduced in 1980, but it took 10 years to commercialize this concept. Still, we are living with the same technology. I don't find any dramatic improvement in the chemistry or the technology wise is concerned. But still, we are using the lithiated graphite or graphite as the anode. And the lithium cobalt oxide or lithium manganese oxide, present day NMC and NCA is the cathode. And organic polymer electrolytes. Organic liquid electrolyte is the electrolyte. So you can think about by means of lithium cobalt oxides and the graphite, lithiated graphite, you can go up to 3.64. The basics behind these charge and discharge is right hand figure gives very clearly its lithium ion is shuttling back and forth between these two electrodes. We are having cathode, we are having anode, and in middle is the separator or was these liquid electrolytes. Then this lithium is shuttling back and forth between these two electrodes. Suppose if you are charging, what's happening from the positive electrodes, it moves to the negative electrodes, lithium ion. While using it, this lithium ion is reversing back to the positive electrodes through the electrode. This is what's exactly happening in your present day lithium ion battery technology. It works well. Concept introduced in 1980, still 2021, we are using the same concept. Almost, I can say 41 years, not dramatic improvement. It's one field where people are not in a position to improve dramatically, not like semiconductor industry. Moore's law is not applicable here. We can understand what's the reason behind this one, in spite of the huge research activities on this lithium-ion battery technology. So before moving towards this one, let us see these pros and cons of this lithium-ion battery. If you ask me the disadvantage of present lithium-ion battery technology, safety is the biggest concern. It arises just because of the potential electronic short circuits of electrons. A classic example has been given, starting from laptop to mobile phone and even Dreamliner Boeing 787, the battery is also. Safety is the biggest issue. It means that people are really worried about using this type of battery for the electric vehicle application is. Then formation of reaction product lines at the electrode electrolyte interface, which people are not in a position to overcome this issue. Since they are using a liquid electrolytes, always there is an issue with the leakage, how good you are having this container. And restriction in achieving higher energy density. Because we are having a problem with the liquid electrolytes, we cannot go more than particular voltage because our electrolyte cannot withstand. So these are the major issues with the present lithium-ion battery technology. So people are worrying a lot how to overcome this issue. So Gooden have proposed in 2010, what are the challenges remaining for rechargeable lithium-ion battery? So this is HOMO, LUMO is one for the cathode as well as the anode, and in between is the electrolyte. So he feels that we have to think about developing a non-flammable electrolyte. A large window between its lowest unoccupied molecular orbital, that's LUMO, and highest occupied molecular orbital, HOMO. Then only you can think about not only 3.6 volt, you can think about the battery with the higher voltage, 6, 7, 8 volts. So we have to think about these high lithium-ion conductive electrolytes. At least the conductivity should be greater than 10 power minus 4 or at least 10 power minus 3 Siemens per centimeter in the electrolyte and also across the electrode electrolyte interface. Do not give large interfacial resistance at the electrolyte electrode. This is the, we can think about this is the way we can improve this electrolyte. Then in the electrode, it's better to design a better anode than carbon. Just people, how long we can use the graphite? We have to think about a much better. Not only the electrolyte and anode, we can also think about the cathode. So design of cathode composed of environmental low cost material that has its electrochemical potential well matched to the form of the electrolyte and allow access to two lithium atoms per transition metal. It's very difficult to realize it. Alpha. So this is a way people are working very hard on both the anode and cathode as well as the electrolyte to realize a high energy density batteries for the future applications. We'll see one by one. If you ask me what is the state of art of lithium ion batteries on the market, so we're using these whether it's a coin cell or it's a pouch cells, stacked cells. So if you ask me what is the status of small lithium ion batteries, it's the limit of lithium ion batteries. I can think about 210 watt hour per kilograms. Otherwise 5777 watt hour per liter. This is the present status. If at all, if you go on improve it, if you replace this lithium ion battery concept by lithium batteries, then you can think about at least 622 watt hour per kilogram. So target of batteries for EV comparable to IC engine is something around 700 watt hour per kilograms. We have to think about from 210 of these maximum possible limited lithium ion batteries to the around 600 to 700 watts hour per kilogram. If you really want to realize a good batteries which can replace the IC engine of your present EV, is it possible to achieve this target? Is it possible to replace the conventional IC engine by means of it? People thought that if you're able to replace this graphite by means of lithium metals, it's possible. But people realized it. But because lithium metal anodes have 10 times the theoretical specific capacity of lithium carbon anodes. Imagine 372 to 3860 milliamperes hour per gram. So if there's a possibility to replace this graphite by means of metallic lithiums, I can get the 10 times the energy density of the present battery. Means that I need not require 10 batteries. A single battery can solve these problems. And again, this low density of this metallic lithium is 0.58 gram per centimeter. And lowest negative electrochemical potential minus 3.05 volts. People thought that, oh, this is the problem with the graphite. If you're able to replace the graphite by means of metallic lithium with the present lithium ion battery technology, with organic liquid electrolytes and whether the lithium cobalt oxide or NMC or NC or lithium iron phosphates, why don't you realize a battery with 10 times greater efficiency? So if people want to replace this graphite by means of this metallic lithium, biggest problem comes now because people are worrying about the safety. The minute you replace this graphite by means of metallic lithiums, then trade starts. It means that through these electrolytes, what's happening? It's penetrated through this electrolyte separator and it just makes the cathode. Just you are short circuiting the cathode anode, so which means that electronic short circuits are sufficient to make a burst. Very dangerous. So just you can see this picture, how it's happening with the liquid electrolytes, how these dendrites propagate through the liquid electrolytes and reaches the other side of the cathode. So once it's able to make a connection between positive and negative, you know very well that what will happen to this then fire. This is the biggest issue. So which means that although the energy density is so high, 10 times, unfortunately, you cannot use these lithium metal with the present organic liquid electrolyte. That's a major issue. But still, people are much interested in lithium metal batteries. Yes, they knew very well that it has the 10 times higher energy density when compared to the graphite. So, can we use some technology by means of which can we use the lithium metal as the anode? I don't want to discuss all the chemistry. Let us take the very simple three technology, lithium metal battery technology. One is the conventional way. I want to use the lithium metal and I want to use these lithium cobalt oxide intercalation cathodes. But I want to use these what you call liquid electrolytes, but I know very well that huge problem I will face. Then with these instead of these lithium insertion electrodes, I want to use the air because lithium air battery is a dream. So without spending money, so I can use the oxygen available in the atmosphere. I can think about the battery. It's nothing but off fuel cell. Then lithium sulfur battery energy density is so high. Sulfur is available everywhere in the India. So can I use my potential to build a battery? That's what you call lithium sulfur battery. So that's the reason why people are focusing so much on these points. So before moving to these developments, R&D activities on the metallic lithium batteries, we can start from the here because the top one is the anodes, bottom one is cathode, the middle is the electrolyte. See the roadmap. We started with the graphite is the organic liquid electrolyte is the electrolyte, and lithium cobalt oxide is this only made it first three combinations. You can see there's a lot of developments in the anode sides, from graphite to the graphite silicon, composites, silicon carbon, and lithium composites. And only people start to realize why don't you think about of metallic? But we just crossed it. People started to work on the anode-free engineering also. That will come back at the end. In the electrolytes, from organic liquid to non-flammable organic liquid, as people worry, because the problem is with the flammable, why don't I make the organic electrolyte which is non-flammable? Or it might be a combination of the ionic liquid and the liquid electrolyte which are non-inflammable. Putting some solvents, I can improve this, what I call this flammability range. Then people working on the polymer, this is the most lot of research activities in India is in polymer electrolytes. And people solid inorganic electrolytes. That's the status now. Again, this cathode, lithium cobalt oxide is the first one, then lithium iron phosphate, then lithium manganese oxides. Then people started to work on the NCA and NMC and lithium rich NMCs. You can see the NMC also so many NMC 532, 622, 811, 955, so many things. So this is the status of this present insertion electrodes. Then people are working very hard to make it sulfur. Then final target is the I hope this roadmap gives some idea about the how people started and different this anode, cathode, and as well as the electrolytes evolution of this R&D activity. So we want to build the lithium metal batteries. We want to use the metallic lithium. By means of which I can increase the energy density to 10 times. That's a concept. So how to use these metallic lithiums? So I can say this one, you can people are working very hard with the conventional technology, liquid electrolytes or ionic electrolytes. But just they used to put some lot of technology. They used to form the in situ solid electrolytes. Right? That's why they're able to manage these potential window of these electrolytes and flammability retardant also. And ex to artificial solid electrolyte interface and stable host for lithium depositions. But I don't believe this could be an intermediate technology, but I don't think it will fulfill this dream of making the metallic lithium as a anode. That's the reason why we have to focus on the right hand side is what you call polymer solid electrolytes. Maybe you can call it the solid, which is not true solid. So only option left out is what is the best technology is the what you call the inorganic solid electrolyte. It means that completely replace the organic liquid electrolyte by means of inorganic solid electrolyte. What does it mean? You can take this present day lithium ion battery technology. So you require a current collector. That's why you are using a current collector. Then graphite. This black one is the graphite. And you are having substance. This blue one is the electrolytes. So this is nothing but a porous negative electrodes. Then ceramic separator, this layer can separate this anode and cathode. Again, it's filled with the organic liquid electrolytes. Then we are having a porous positive electrodes. Might be the lithium cobalt oxide, lithium iron phosphate, or NMC, NCF, whatever. And you are having a current. Both the sides current collector, then you are having these liquid electrolytes completely filled everywhere, and you are having this one side is porous negative electrodes and porous positive electrodes in between the polypropylene separators. This is the present day lithium ion battery technology. So what we are proposing is we want to replace this graphite by means of this metallic lithium. So completely remove these ones, made the metallic lithium it's a solid. So I want to improve the energy density, so which means that I want to use the whatever the best way. I can think about any electrons. Lithium cobalt oxide, NMC, NCA, have sulfur. If someone can find a new electrode, also I wish to utilize it, maybe 6-volt cathode. Which means that I cannot use the present day organic liquid electrolyte soap polypropylene separators, which means that I wish to replace this liquid electrolyte based concept by means of its solid electrolytes. Again, I am interested only on the inorganic solid electrolytes, which means that so lithium is solid, metallic solid, electrolyte is a solid, and the cathode is also solid. Then people start to name it as the all solid state lithium battery. So you can say this biggest advantage is because we are completely removing this flammable organic liquid electrolytes. And actually, you can think about safety is the best one. So you can replace this most of this space by means you can reduce this space, which means that you can minimize the size. What you call even with the insertion electrodes of lithium cobalt oxide or lithium iron phosphates, volume advantage. The insertion electrode with sulfur with oxygens, so no flame. So which means size has been dramatically decreased and energy density has been improved, and as well as the flammability has been completely avoided. That's the reason why this solid state battery technology is so popular with the present days. If you ask me what are the advantages, the simple structure. So you don't require any separators. Which, if you're able to find a suitable solid electrolytes which can enable the use of lithium metal anodes. So naturally, decomposition voltage of solid electrolyte is expected to be high when compared to the conventional organic liquid electrolytes. So high energy density you can imagine. So non-flammable nature of the solid electrolytes helps to improve safety of the battery. So once you understand everything and improve the technology, actually you can simple structure, 3 layers of solid electrolytes and 2 current elements. Complexity has been removed dramatically. Simple structure and simple manufacturing process. So naturally you can expect mass production. You can dramatically reduce the cost of the battery. Which means that everything, because you are having a cathode, you are having the anodes, but because you're using metallic lithium, I don't have any much trouble. The only problem is if at all if I want to realize a all solid state lithium battery means I have to develop the solid electron. So what is the characteristics required to develop a solid electrolyte? The solid electrolyte should have high ionic conductivity at the operating temperature, which means an ambient room temperature, not at the 600-degree or 400-degree high temperature. It should be chemically stable in contact with both the positive and negative. It should be stable against metallic liquids. It should be stable against the other sides of the cathodes. I'm going to use it. So negligible absence of electronic conductivity for a wide range of lithium activity and temperature, which means that my electrolyte should be a perfect ionic conductor, where electronic conductivity is very minimal. My transference number of lithium transfer should be around 1, very close to 1. And electrochemical stability. Above all, if you want to use it, you have to think about of low cost, safe, easy preparation, and environment friendly. Then only you can compete with the present day market. So many characteristics. Very difficult to find all the characteristics together like human being. We will have some defects, some like, but is all the electrolyte should be, if you really want to develop a perfect electrolyte, then you should satisfy all these conditions. Otherwise, I don't think you'll be in a position to serve. So before moving to the solid electrolytes, we have to understand some basics of solid electrolytes. Even a big scientist also 10 years back, they asked me how solid can conduct. Only liquid will electron, because solution chemistry is very strong in our part of the country. Lot of beautiful and high standard electrochemistry, solution chemistry. But solid state electrochemistry, very, very less. Knowledge is very limited. But the solid electrolyte, ionic conductivity in solid is not new to the world. Anything? Prasad? 1839, this Michael Faraday, the first solid state electrolytes, lead fluoride conductivity is so good at high temperature. And Warburg in 1884 demonstrated sodium ion conduction in glass. Again, Warburg and Techitema in 1888, first measurement of transparency number. And great credit to the Nernst again in 1900, discovery of Nernst law. Ceramic rod heated to the incandescence. Then it's about solid oxide fuels and oxygen gas sensors. 1914, high silver conductivity, silver iron at 150 degrees Celsius. And sodium sulfate battery in 1966, things goes like this. First polymer Harman has contributed great contribution in 1973 on polymer electrolyte. These are the evolution of these solid electrolytes. But I can give a very simple way to understand this difference between the liquid electrolytes and solid electrolytes. If you look into the sodium chlorides, just dissolved in water, the conductivity is 10 power minus 1 Siemens per centimeter. But if you take a single solid sodium chloride, single crystal, conductivity is 10 power minus 12 Siemens per centimeter. Its conductivity is 11 times lower than the conductivity as a solution. I hope you can understand. And what would be the problem with the liquid electrolytes and solid electrolytes? So really, if you want to have some application point of view, your solid electrolyte should have conductivity very close or minus 3 Siemens per centimeter at room temperature. Otherwise, we're keeping 10 power minus 12 or 10 power minus 10, and what we're having 10 power minus 2 at present cannot match. At least 10 power minus 3 Siemens per centimeter. Then how to improve the ionic conductivity in solids? This is a simple expression. Sigma equal to summations Qi, mu I, the high. Qi is the charge in coulombs. I is the concentration of defects, number of defects per centimeter cube. Then mobility of these ions. So ionic conductivity, both the cation and anion conductivity, starting from proton, lithium, sodium, oxygen, means that defects is the major things. It might be doping or substitution, or might be intrinsic disorder or space charge, by means of which you have to create some defects, by means of which you can think about the conductivity in these materials. Which means that to move through a crystal, it must have from an occupied side to the vacant sides, like this. So which means that if the system is completely filled, atoms are arranged perfectly lattice, if there is no gap, if there is no vacancy, I don't think you can able to find any connectivity. Which means that if you have some defects, then there is a possibility that ion can jump from the one side to the next side. All of you know very well that basic solid state physics, you might have come across the Schottky defects and Frenkel defect. Sodium chlorides, you might have seen these Schottky defects. In silver chlorides, it's interstitials. This is the Latin side itself, you can find the vacancy. Since we're having a vacancy, if a crystal has something like a Schottky or Frenkel, then there is a possibility of this ions can jump from this one side to the vacant side, then you can think about the conductivity. So vacancy, here sodium jumping to the vacant side here, called vacancy conduction. So it's called a cation and anion vacancy pair is a Schottky defect. Then in this case, interstitial conduction, because we are having a silver here, and this just makes a move from here to here, and finally it makes a diffusion. It means that as the temperature increases, the defects increases. Whenever there's large defects, the conductivity will be improved. This is what you call Arrhenius relations. So it tells you very clearly you should have some defects, larger defects, and you can easily think about the conductivity. So in the movement of sodium ions, in sodium chlorides, this is just because of vacancies originating from Scott-Cative. So here, if you look into these ones, these sodium ion must squeeze through the lattice, inducing significant local distortion or relaxation. Just like the derivative, it pass through these bottlenecks, which limits the mobility of ions. Sometimes instead of going to the forward, it can backward also. If it makes a jump back to its original position, leading to a net ionic migration, no net ionic migration. So in the unit cell, if you take it to get across the unit cells, here if you take this is the unit cells, to just come out of this unit cell to the vacancy, sodium ion must off from the center of the cube, and it squeezes by 4 chlorine, and just it wants to make comes out from here. Naturally skews, then somehow it has to overcome all the things, then it has to make it jump from here to here. So the energy of this transition states will determine the ease of migration. So the frontal defects in AGCl can migrate via two mechanisms, direct interstitial jumps. This makes a jump like this. So another one is just silver comes to this one, and it makes a transition here. Like that, you have to understand how these ions can make a jump. Again, this zirconium oxide ion conductivity. We used to measure this 10 power minus 4 Siemens per centimeter square at high temperature. It restabilized to zirconium. Which means that mobility, natural amplitude of the energy barrier to shift from one side to another. This is how much to move from here to here, how much energy I have to overcome. It is a structural factor, geometric constraint to enter the site. Then it's electrostatic interaction with neighboring ions, free volumes, polarizability. So many factors will tell you this, how much difficulty it has to overcome if you really want to make a jump. So which means that if you want to improve the ionic conductivity, you have to think about somehow you have to make this high mobile ion concentration. Then high number of empty or vacant signs for ions orbiting. So small activation should not spend so much energy to overcome these barriers. Small activation energy for conduction. Then high number of conduction channels, not only a single one dimension, but it could have the 3-dimensional channels. So naturally, amorphous conductivity people are expected to be more when compared to the crystalline. This is again same way. So people are working very hard how to improve the conductivity in solid electronics. Again, as I told you, it's not new. We are having several lithium-ion conducting solid electrolytes, but just not the 10 power minus 6, minus 7, minus 8. We need some fast lithium-ion conduction at least 10 power minus 5 to 10 power minus 3 Siemens per centimeter. We're having so many materials. Lithium-ion, beta alumina, nazican, bisican, glassy, APS, so many families. But the most competent people are really interested to fabricate is all solid-state lithium batteries. It's completed sulfides and oxides. Because you really want an electrolyte which should possess the high lithium ion conductivity, wide electrochemical stability, good mechanical properties, simple processability. Just combine all these things. This is the ideal solid electrolyte. Then lower cost, higher capacity, that's a different thing. But if you look into these two, and sulfides, this family is matching with it one. These are the characteristics. And oxides, somehow you could satisfy this. So sulfides and oxides are the most relevant material for the realization of the all solid state lithium batteries. So now we can move on to these ones. So what is our journey into the invention of fast lithium and conduction in lithium garments? What made us to enter into this field and where we stand and what is our contribution for the development of all solid state battery? So I wish to start our research activities was under the University of Kiel in Germany. Did a lot of work, physics. Then with the Toyota, we have done the next stage of work. Then with the process good enough, we understood this what is the optimal lithium concentration. We get the maximized lithium ion conductivity, lithium cortex. Then we did last 10 years, we did a lot of work in this high energy density battery lab in Pondicherry. Starting from synthesis, interfacial engineering, lithium sulfur battery. At present, we are working on anode free. I wish to touch upon simple things. I don't want to discuss in detail. It's very difficult also. You have to understand what is the progress made, how this progress has been made to realize the all solid state battery based on lithium carbon. As I told you earlier, we are much interested in oxides because it has its own advantage when compared to the sulfides. Oxides mean processability easier. You can make it in a very bulk. You can easily make the tapes and so many advantages. That's the reason why people are much interested in the oxides. These others can mute the mic. Okay. So we're having the 4 electrolytes, several hundreds of electrolytes in oxide form. People are much interested in these 4. They thought that these 4 electrolytes are ideal for the fabrication of all solid state batteries. One is the LiSiPo. The next one is the LiPo. Third one is the Vagara, this what we call lithium, titanium, germanium, silicon phosphates. The perovskites, lithium, lanthanum. If you look into this graph, this is called Arrhenius diagram, which tells you very clearly ionic conductivity of the perovskites, lithium, lanthanum, titanate is very high, and this LiSiPo is least in between these two. But if you look into the stability, the LiPo and LiSiPo, you can make the battery with something around the 5.5 or 6 volt battery also be able to find a suitable cap. But stability for this Vagara and lithium titanium oxide is least. So one thing is very clear, the conductivity is so good, stability is poor. You cannot make the battery with the higher voltage. But conductivity is poor, but you can make the much wider potential window. So God played a big trick over here. If you're able to give the good ionic conductivity, reduce its electrochemical stability. Material has the high electrochemical stability means you reduce the what you call conductivity. Which means that that's the biggest problem people are facing for the last 100 years to find the suitable electrolytes, both higher ionic conductivity and as well as the good electrochemical stability. Means that successful identification of suitable solid electrolytes with good conductivity and good chemical stability. That's our target. We entered into this. So we want to design a new solid electrolyte which possesses all the basic characteristics required for the fabrication of the all solid state lithium batteries. Just now we have seen these perovskites, lithium lanthanum titrates. It's a good conductivity, but only problem is the chemical stability. So if the lithium is there, lanthanum is there, oxygen is there, only problem is titanium. So that's easily it can be reduced by metallic lithium. It becomes titanium 4 plus to titanium 3 plus, then electron, excess electron, which helps to, that's why problem happens. So we just looking in the literature, we found here these materials. This composition is like this lithium, lanthanum, and M2 here the niobium, tantalum, and antimonite. There's no titanium. This is what you call people propose this could be a garnet-like structured material. But these people, reported people are the pure inorganic chemists, just they're interested in structural aspects. They unfortunately they didn't measure the conductivity of these materials. But once we realized after working a long time with these perovskites, thought that why don't we think about the some other materials? Fast lithium ion conduction limited only to these earlier 4 materials. Why don't you think about your new structure? Maybe other than ferroskates, silicon, nasicants, we can find some other structured materials can give much better ionic conductivity. That's the reason why we focused on garnet structured materials, and composition is very similar, and there is not titanium. Just with curiosity, we measured this, what you call this conductivity of this material. Out of the 3 combinations, niobium, tantalum, and antimonite, because these are the 3 way people report. So very simple steps by means of just solid state reaction, mixing these lithium hydroxides and lanthanum oxide, niobium oxide, stoichiometric ratio within at this 900 degrees Celsius, we could get the single phase materials. When you measure the conductivity at something about 10 power minus 6 Siemens per centimeter, it's not so good, great, but it's not bad. You're able to demonstrate the fast lithium ion conductions. But only problem is what we are expecting is 10 power minus 3, but what we are getting is 10 power minus 6. Is it possible to improve the conductivity in these lithium garnets? So that time I entered in this process after labs. So I don't have any great knowledge on these topics, state chemist. Even I didn't know how to make this stoichiometric ratio for this. Already tantalum, niobium, and antimonite has been reported. But just in curiosity, I included bismuth in this series. People started to laugh chemists because strong chemists they have a great idea. Bismuth cannot sit in the 5 valence, but it might be in 3 valence. Being a physicist, and I don't know, great idea. Just I included by God grace, I could stabilize in 3 weeks. The idea is I wish to do a systematic way to find what is happening in these systems. So when I replace this tantalum, niobium, antimony, and bismuth, 4 compositions, I found that the bismuth garnet structured materials shows the best conductivity. Then if you look into this cubic lattice constant, I could find this Draper system as the higher lattice parameter. The reason is very clear. When having this tantalum lower ionic number, and niobium is slightly higher, antimony is much better, and bismuth is a larger ionic radii. So when I replace this by means of larger ionic radii, I could increase the lattice constant by this way. I could do something, just I ease out these bottleneck sizes. So by means of which lithium ion makes a perfect gem, so it could improve the conductivity. This is how we got the best lithium ion conductivity. But always we have to check where we stand after making these materials, because already 4 competitors in this market. So just a 2 step ahead, but still so many materials are above us. People will laugh if we say that we are able to make an invention which is a good ionic conductivity. So what we did, how to improve this conductivity? This is our starting point. So I made a systematic, so just what I did is what you call polyvalent substitution. I replaced this trivalent lanthanum by means of the one divalent. So remove this La lanthanum, I put some divalent. I'm putting this magnesium, calcium, strontium, and partly strontium and partly barium and barium. Again, this my prediction comes out very great. So whenever I am a larger ionic radii dopant, I could expand the lattice by means of which I could get the maximized lithium ion conductivity. So you can see here earlier when I had lithium 5 and here when I have the lithium 6, I could jump further. So still 2 more competitors. So I want to be number 1. What I did is it possible to further improve this one? But before moving this one, we have to understand what is the reason for getting this maximized lithium ion conductivity in these garnet structured materials. So with the available powder oxide action just simulated, we found a 3-dimensional pathway in this material, which is very interesting. It's not like a 1-dimensional pathway of lithium ion dynamics. What we want is 3-dimensional pathway. It's very encouraging, but by the time people started to understand much better, secretary should go to the Professor Cousin from Essex University, a strong structural chemist. By using neutron diffraction, he able to propose a new structure. What he called this. What we thought initially with the powder extra diffraction is lithium is housed exclusively in octohedral body. But what we found here is lithium is housing not only in the octohedral coordination but in the tetrahedral coordination. Very interestingly, what we're having is partial occupancy in the tetrahedral and partial occupancy in the octahedral. That's the reason why the jump is very clear. You are having more vacant sites, lithium migrates very easily. This is the one interesting and important contributions. It helps us to think about something else. This is how just we replaced one more things and we end up with this zirconium containing lithium garnets with 7 lithiums. Very simple way. This is our evolution of this family of garnet structures, solid lithium and conductors using these. I think, yeah, you might have seen this very good laser material, yttrium aluminum oxide. From this one, we replace this by means of this one, and slowly from Li3 to Li5, Li5 to Li6, Li6 to Li7, we could found a interesting materials. If you look at this after plotting this one, our LLZ shows the much better conductivity than any other materials. So what is our target is be able to achieve the highest lithium ion conductivity. But what we require is the chemical stability, particularly stability against the metallic lithium. So we don't have great facilities in 2007 in Germany. At that time, the key level, what we did is just we took the molybdenum crucibles and put some metallic lithiums and melt it because molten lithium is highly reactive. Then we placed our sample, this zirconium containing lithium carbide. Earlier than none of the material is stable against no oxides until then stable against metallic lithium. So this is the first material which is stable against molten lithium for months together. Which tells you that so just this material is highly stable against metallic lithium. The reason is simple because this, if you look at this framework, it's made up of the lanthanum and zirconium and oxygens. The lanthanum is a trivalent large ionic radius. Diffusion coefficient is very small. It takes years to gather, if at all, if you want to make a diffusion. Then again, zirconium is a perfect 4-valent. You cannot reduce it just like that. So it's also massive ion. So it takes longer energy to diffusion. Means that so naturally it should be a lithium migrations only, which gives a yeah. So it's really important thing in the fast lithium ion conduction. So this material satisfies almost all the basic criteria required to develop the all solid state battery. Stability against metallic lithium. Very good lithium ion conductivity. Wide electrochemical window afterwards in Toyota labs we checked. It is stable even after 7 volts. So which means that you can build a battery with more than 7 volts. So then we compared where we are spider webs, then our garnets is much better in several aspects when compared to the remaining solid electrolyte. So this invention made in 2007, I came back to India, I became the director, I not only research activities, but world struggled to make these materials. Because every labs they end up with this, what I found is the cubic structured materials with the conductivity of 10 power minus 4. But others, they able to stabilize only in tetragonal, they never bother about the structure. And conductivity is 2 order of magnitude higher than the cubic structure. People started to find fault with me, which made me think about resigning this good position. Came back to the Pondicherry University by the time I moved to the Toyota labs in Japan. Then we understood what is the reason for getting these what I call these cubic phase during my synthesis and other people stabilize only in technical state. I found that because when I'm sintering the samples, being a physicist, I don't have any fear over sintering the samples at 1225 degrees Celsius. Chemists always will fear to sinter at the much higher temperature, which made us to 1200. What's happening here? Because I used alumina crucibles, most of the Western labs they used platinum crucibles. What's happening here? And I sintered at 1230 degrees Celsius for 36 hours. Aluminum ion from this what we call aluminum crucibles diffuse into the my pellets and replace some of these lithiums, which means that incorporation of the aluminum ion from these alumina crucibles able to stabilize this what we call cubic. Others, if you are unable to replace some of these ones, more lithium means you will stabilize only in tetragonal structure. So this we understood, but chemically we didn't also. But I wish to point here just our journey from this lithium 3 to lithium 7. Ionic conductivity is at 600 degrees 10 power minus 5. But when you enter the lithium 5, this steel cubic structure at 30 degree 10 power minus 6. Then when you have the lithium 6 at 10 power minus 5 30 degree. And at 30 degree once again 10 power minus 3. This is how we move from this very poor conductivity to the best demand energy. But even this Li7 also people started to understand what are the different crystal structure or small difference. I don't want to discuss much, but still a cubic structure. And how the conductivity able to improve it. This is what I told. We're having this lithium 3, it's a block 1. Purely tetrahedrals. But here in Li5, just opening up the tetrahedral as well as the octahedral coordinations. Then the mixture of these two really helps me to understand to improve the conductivity. Then we are given a reasons how this conductivity improved by means of moving from Li3 to Li7. Then with the process good enough, I understood what would be the optimal lithium. Because I have gone up 7, can I go up to 8? No. 6.4 to 6.6 is the optimal lithium concentration to get the maximized lithium ion conductivity in this. Then whole world able to understand this concept. There are a lot of research activities on this particular. If you look into this one, this is the way from 2003 to this 2019 or 2020, how this evolution of this garnet structure lithium. And you can see biggest breakthroughs. What is our contribution? Where we stand now? Huge research activities based on the experience. If you look at this figure of merit compared to this competitive sulfides, antiperovskites, and borohydrates and hydrides, our figure of merit is 22.5. Nothing is matching with us. And the greatest advantage is you can make the freestanding membranes like this, tapes like this. That's the greatest advantage. It really changed the world now as far as the remaining electrolytes. That's the reason why a lot of research activities on materials. But I wish to focus on synthesis also. Many people, because imagine once you want to commercialize, you know the techniques by means of which you can produce in the mass level. So, what are the different techniques? Is a more suitable technique for the industrial scale of. So, when I entered Pondicherry University in 2010, I don't have any great facilities. So, just how to start with the works with the beaker and the magnetic stirrer, small furnace with other labs. Just this is a way. So, because why you have required a very high temperature? Because industry may not like to go for very high temperature, which means the capacity involved is large. So just we prepared this material to much higher temperature by means of what we call the simple soldier techniques. We are able to develop these techniques and almost for all the garments we are able to make this material by means of simple soldier technique at a much higher, around 900 degrees Celsius. Then we use these other techniques also, this combustion. I like it very much. This is a very fast process because other techniques will take a week. This within 2 days you can end up with this material. But the only problem is people may not like these techniques. The industry may not like this because the combustions can see huge amount of fire and reactions. One of advantages the simple, fast, low cost, and low temperature process. Nanoscale powder, you can just like a fume. Size will be something in few nanometers, homogeneous. But unfortunately, that's fire, this combustion during the reaction is the biggest problem. But still, think about these techniques for making the very fine particles combustion process. And this is the two techniques for industrial purpose. People thought that by this way continuous process, they can make the homogeneous nanoparticles also, stabilized spray pyrolysis and flame spray pyrolysis. But we tried with these plasma techniques also. But it's not so successful. But success has come with it's what you call this RCA Hyderabad. So we are able to prepare a material by means of this plasma. Not only that, we can pour these materials on a substrate. And essentially, we could see the color changes. This is how we started to understand. So you can do it by means of these other techniques. From industrial point of view, And people are working on these membranes. This is the conventional way of making these membranes. So just mixing it up with these polymeric films and stirring and transparent solutions by putting syringe, then just make the membranes. Fiber. This is simplest way, but for the lab scales we can take this type of material. So just I'm talking about the what are the ways by means of which we can produce these carpets. There are several techniques. Depends upon the application, depends upon the scale. Industrial scale means what would be the ideal technique to make the tons of powders. People start to realize, find a technique, suitable technique for fabric when they making this garnet powder. Although we achieved 10 power minus 4 Siemens per minute, still people are want to improve this conductivity. We have done this grind boundary engineering. This is the biggest problem with the hots. If you take the lithium lanthanum titanate perovskites, this grind, this single grind, single crystal's conductivity is something around 10 power minus 3 Siemens per centimeter. But if you take the total conductivity, because we are made up of so many grinds, in between we have a grind boundary, total conductivity comes up to 10 power minus 5, which means a 2 order of magnitude lower than the conductivity of the single grind. It means that your grind boundary conductivity also should be improved. Otherwise, resistance should be reduced to get this, improve this total lithium conductivity. Ultimately, in galvanic cells, that is going to determine what is the total conductivity. So, just this is the one way by means of which what you call lithium aluminum silicates, this glassy and amorphous asphosine nanocrystalline phase, enclosing at the grind boundary, we could reduce dramatically this grind boundary and comes just what you call the improve this conductivity. So we used a different sintering additives because electrolytic mixtures and what you call the liquid phase sintering process. Along with these garnets, we had lithium borates, lithium phosphates, and lithium silicates, and you can see here after adding these ones among all these lithium borate and lithium phosphates and lithium silicates, really helps to improve this density. So you're able to improve the density very close to 98 or 99 naturally grind boundary. It's almost like a sheet, a single crystalline sheet. Grind boundary is less, so naturally you can expect the less grind boundary resistance. So we could reach something around 10 power minus 6. One techniques of grind boundary engineering. And really, from an academic point of view, is it possible to improve the conductivity much better? We use the simple what I call spark plasma sintering technique. We could improve the density by means of which we could improve the conductivity. And also we used a techniques what I call this hot isotopic press at the spark plasma with the NPL and hot isotopic press with the IG curve. That is some collaborative work on the project also. By means of this hot isotopic press, we could able to demonstrate it by enclosing this what I call the liquid phase sintering, these agents, improve the density. We could, I think, completely fill with this what I call this lithium silicate, by means of which we could able to improve the total lithium ion conductivity, also reduce the interfacial resistance. This is our contribution for this particular grind boundary engineering. Then people started to ask, you are claiming that your material has the good lithium ion conductivity, it has the good electrochemical stability. What's happening? Why don't you make the battery? We also attempted. We thought that we had a great facility at that time in 2007 in Ministry of Care for making this all solid state battery. So when I got an opportunity to work with Toyotas, then this is the battery made in 2010 in Suzuka University. So we used a PLD for making this LCD, power splittering for current counter, the thermal operator inside a globe box to make a thin film of metallic lithium. This is the first solid state lithium metal battery based on carbon structured electrolytes made in 2010. Lithium one side and lithium cobalt oxide other sides in between is a solid. This is our dream. Our dream come true on fabricating solid state battery. But if you ask me what's the results, it's highly discouraging. We never thought that we will end up with this. Even we are not in a position to blow our LED lamp. Just we have to draw only microampere current. Just we are able to demonstrate this charge discharge. So then we understood it's not a question of just identifying or developing a suitable solid electrolytes. we're having so many greater hurdles, practical hurdles. That's what we call solid interface. Which took a lot of time to understand this one. This cathode solid electrode interface and anode solid electrolyte interface is the biggest bottleneck in commercializing and realizing the all solid state lithium batteries. If you ask me, generalize the things, what are the common issues? It's a common issue is both the interfacial resistance of the anode solid electrolytes as well as the cathode solid electrolytes. Lithium dendrites, we thought that the biggest advantage is having just the solid electrolytes can barricade the lithium dendrite. No, it's not true. And stability is the biggest issue. And sometimes when you use the lattice mismatch, then cooling off after a few seconds. Then space charge layer gives the huge problem and making a large interface. So we are having the issues with the anode and issues with the cathode, and we realize so just we have to solve the problem one by one. Not only if we can find the solutions, then we can dream of making the all solid state. So that we understood what are the issues with the anode sides, because ultimately we want to use the metallic lithium. If at all, if you want to think about it, first let us try to solve the problem at the anode side. So strategies for the one by one. Overcome the dendrite issues related to the lithium metals. So the grind boundary engineering, we did some lot of grind boundary engineering, putting some layers and buffer layers, putting some coating on these carbon electrolytes and putting metallic lithiums, then anode free structure. These are some strategies people use. Not only these grind dendrite issues, but major issues the grind and the interfacial resistance. People started to work on surface treatment, just removing this, what you call the high resistive lithium carbonate layers and tailoring grind size, operating at high temperature, applying pressure, buffer layer, three-dimensional structure, alloy anodes, and finally anode free structure. This is one of the highest. A lot of people really worked very hard to develop all these technologies. We also contributed a lot initially. Just we introduced what we call the gold in between this metallic lithium and carbonate electrodes. And slightly at the high temperature, 180 degrees. We could able to form the lithium gold alloy at the interface. You can see these white portions by means of which, just imagine, initially the interfacial resistance between the metallic lithium and solid electrolyte something around 8,600. We could reduce it to something around 54 ohms per centimeter square. Now people able to reduce it to 1 ohms per centimeter square with atomic layer depositions. Believe it or not, the interfacial resistance between the liquid electrolytes and the what we call the anode, and at present what we are having is much lower. We never thought that solid interface we can produce this interfacial resistance by means of this. But not only a buffer layer, we used a lithium niobate, another layer also. It's not only this gold, it's metallic. We used the ionics, lithium niobate. By means of which, introducing a lithium niobate layer, we could able to reduce the interfacial resistance dramatically. At the same time, we were able to what we call improve the critical current density up to 360 microampere centimeters. Not only gold metal or ionic lithium, but we used a graphite. We could able to improve this critical current density something around 750 microamps per centimeter square. So we used it several ways. Then we have finally ended up with this alloy. Why we have to use only metallic lithium? Can we think about adding a small amount of lithium zinc? We could able to increase the resistance 7.5 ohms per centimeter square. Not only that, we could able to improve these what we call the critical current density dramatically. So people are working very hard, starting from these metals, non-metals, and ionic materials, and even alloy anodes, by means of which they were able to reduce the interfacial resistance. At the same time, they are able to improve these what we call the critical current density. I can say we don't have any major trouble at present in handling the metallic lithium. So this is another way by means of putting this what we call this on the polypropylene separators, just in niobium metals. By means of these other strategies, the conventional polypropylene separators, we put the metallic layers and niobium layers. we could reduce these problems. That's a different thing. These are the interface strategies of the garnet solid electrolytes of the game and how people are able to improve it. This is the story we'll tell you about this. So really contributed a lot for this sector on the anode sides, metallic lithium sides, and they're able to reduce the grind and the what you call interfacial resistance and as well as the input density. See here 1 ounce per centimeter, 5 ounce per centimeter square. But the major issue at the cathode, we never thought that we'll have this many issues at cathode. Everywhere, we're having issues with the reaction product layer, space charge layer, elemental core deficiency, volume expansion, lattice mismatch, and over contact. Oh, it's a big part that we will face much problem with the anode sides. Unbelievable, huge issues at the cathode. Then, a lot of strategies have come forwards to overcome the volume changes 3D cathode host. To reduce the space charge, we reduce the hot interfacial layers. Stability issues put the cathode coatings, over contact wetting interfacial layers, and lattice mismatch compatible structures, and buffer glassy layers and core deficiency. Several strategies people started. It's really complex techniques we use. But all the credit should go to our earlier work in 2011. We able to found that a diffusion of the cobalt from the lithium cobalt oxides, which helps to form the lithium zirconium oxide. The action product layer with the cathode and solid electrolytes, it gives large troubles. That's the reason why the battery fades after. And to overcome this problem, people started to work on these several things. We also did with metallic layers. We tried with gel polymer electrolytes, between cathode and solid electrolytes. We were able to demonstrate, we were able to improve the cycling performance. Even up to 100 cycles, 500 cycles with just theoretical capacities matching. So not only that, we have many lot of work is on there. So we used a lithium silicate buffer layer over garnet, by means of which we could able to demonstrate the working of a battery. But it requires a lot of improvement. That was a huge research activities needed and it's going on to overcome this problem. And we did a lot of work on the lithium sulfur batteries. Because the issue is the what you call polish sulfide. We thought that when you use the liquid electrolytes, it's a problem, but if you move on to the solid electrolytes, you can block the settling effect. So that's the reason why we entered into this lithium sulfur. If you're interested, please go through the slides so you get good information. So if you ask me why lithium sulfur is lower cost, availability of sulfur is huge, high theoretical capacity, this works this way. But the major issue is this is the because dissolution is starting from Li to S8, Li to S6, Li to S4, Li to S2, Li to S, so many complex limitations. Limitations, the cathode is the sulfur conductivity is very poor. So dissolution of active materials, passivation of insulating Li to S at the finally. So electrolyte present, conventional electrolyte solvent of polycell interaction, shuttle mechanism, viscosity variations, and anode is mossy lithium unstable interface. This is the problem why people struggle a lot with the lithium sulfur battery. We also did a lot of work on this one. We changed this concept of using the sulfur cathodes. We slightly modified the synthesis techniques of making sulfur cathodes. And we demonstrated with our garnet this bucking up this polysulfide shuttle. Not a great results, but at least it shows that it gives us information that if you use a solid electrolytes, you can overcome the problem of this what you call polysulfide settling, which means that just not allowing this polysulfide to cross the barrier of this garnet electrolyte. So we have done this a little bit of the conventional PP separate, how this garnet coated on the conventional separators, still with the liquid electrolytes can use it yes, without separator on the LLZ coated separator, it goes shuttling takes place. But when you coat it with this LLZ, we can able to remove this shuttling effect. Which is very good. But lithium sulfur batteries really active, lot of these activities are going on. If you can look into this one, various activities on the strategies to overcome the cathode garnet interface. So this is I'm at the end of my talks. So this is our current activity. So what we are interested in is just why the problem is handling metallic lithium. Is it possible? This is having a right material, garnet structure, solid electrolytes, and some cathodes. Is it possible to realize the what you call the anode phase engineering? So what you're having is just a garnet and current collector above a current collectors. Then we can think about it. So what is happening during charging? What will happen in situ from these cathode sides we are pushing the lithium ions and entering here on the other sides, just forming this in situ lithium metal. Reverse is the case. One doing the discharging, this lithium goes back to this cathode. You can ask me what is the greatest advantage of this one? The advantage is simple. If you use the conventional solid electrodes, 100% is volume. Just by reducing this graphite by means of thin metallic lithium, I can reduce this another 35% reduction in the size. Which means that 35 reduction means I can have one more cell. So, but if you replace this metallic lithium and avoid the problem with what you call this metallic lithium, so I can reduce something of 50%. I can save 50% of this. The energy density is same. Which by this way, that's the reason why this anode engineering is a very hot topic. If you ask me advantage, still it's a solid electrolyte. Increase safety. So it enables lithium metal as a anode just by means of pushing the metallic lithium from the cathode to here and into the formations. Still it's a lithium metal batteries. Which means it enables high voltage cathodes because solid electrolytes I can think about any new electrodes, not only NMC, NCR, whatever it may be. I can think about something else. So size has been reduced 50%, so naturally smaller size, high energy density. Since I'm using this metal garnet such electrolytes, I can think about using this battery in tropical condition like India for 60-degree also. Longer lifespans.
Just tell me which topic is finished. Anybody?
Hello? Hello? Hariprasad?
Sir, you can continue, sir.
So it's increased safety. So just I'm going to wind up in another 2 minutes.
Yes, sir. Yes, sir. Okay.
So this is the advantage. So if you ask me what you're doing at present is just we are making this preparation of dense garnet tapes. Pouring it in garnet powder with that once just we're making a tape casting. Then after making this dense garnet tapes, just preparation of garnet scaffold. We are making these small scaffolds. Then introducing interlayer and current collectors, other sides. Then we are reversing it back, then filling the scaffold with the conductive ink because we want to improve this what we call the electronic conductivity. So the scaffold will have ionic conductivity, just this ink will produce the electronic conductivity. Then we will introduce this what we call cathode, and putting current collectors. This is how a single shells what we call these spots. If once we success, then you can think about the multi-layer. Then his take sets. That's our hack focus on making these all solid state batteries based on garnet structure electronics. So okay, I'm thankful to my boss, Mr. of Kiel, who has done a lot of contribution for all my success. Starting from doing my research, start my research career in electrolytes. And Professor Iriyama with his Japanese counterpart who helped me a lot. University has University. And very short time with Professor Goodenough, I learned many new things. Once again, thank you to all the three big people. So I should be thankful to my research teams, who all the people are present. Then three big industries, applied materials, farming, undistributed startups, then HDL is working now. Then DST Sub, BRMS, AICTE, AICSR, DST, DRDO, UGCC. So many people really helped to build the lab. So I'm thankful to Anand. So I'm happy to be here to answer a few questions.
Yes,
Thank
sir.
you. Thank you very much.
Thank you, sir. Thank you for your illuminating and enlightening lecture on this very pragmatic topic. Hope this session is very useful. Now, I would invite the queries the queries you want to ask. You can just put in those questions in the chat box. So if you have any doubts, that's fine. Very informative.
1 minute, madam.
Hello, ma'am.
Yes, sir.
we will go for open. So somebody can raise the hand, they can ask. So Ajit Kumar
Yeah,
is
yeah.
asking some question.
Yes.
So we will allow to him
Yeah.
to ask the question.
Yes.
Yes, Ajit Kumar sir.
Hello, ma'am. Hello, sir. Yes, sir. Yes, sir. Good morning, sir.
Yes, sir.
Hello.
Please
Yeah.
ask the question.
Sure, sir. Sure. Hello, Professor.
Yeah, please tell me.
Yeah, it was very interesting talk, Professor. So I had some a few doubts on the talk. Sir, you were talking about the interfacial resistance, no, sir? So you have introduced the gold interlayer between cathode and electrolyte. So how the ionic transport will be enabled if the metallic interlayer presents in between two layers, sir?
So what's happening here? Just we are making as a gold, lithium gold alloy. Once you put in gold, it's not a pure metallic, it's a barrier. Just we are making an alloy. So once you heat it at 180 degrees Celsius, the metallic lithiums, and not only that, when you diffuse it, it will form a alloy. So this alloy helps to overcome the interfacial resistance. Not the gold is the helps to overcome interfacial resistance, because it will help, because if you don't put anything, you will have the lithium carbonate, the high interfacial resistance.
Okay.
So once we put this, because it's very smooth surface. So lithium diffusion is what we call the homogeneous current carriers. Helps to overcome this lithium dendrite, as well as it will help to overcome this interfacial resistance. I think if you look at this paper very detailed, we can get this what is the mechanism behind when you have the metallic layer, when you have the inorganic layers, when you have non-conductive layers, and when you have these alloys. So it's a purely alloy concept. It's not the metallic layer.
Okay, sir. So it will be like it will enhance the transportation of the ion between the two cathode and electrolyte, right, sir?
Yes. Solid electrolytes and the anode.
Okay, okay, sir. That's great. Sir, and I would like to know how we exactly predict or calculate the interfacial resistance from impedance spectra, because unless we measure the spectra from the full cell, so often we get maybe one or two semicircle. When we fit it, so which part we need to consider? Maybe most of the cases it won't appear. It is singly, it will show like a single semicircle. So how we face this problem, sir?
I think you just look at this all our papers. We have mentioned very clearly with the symmetric cells how careful you are making a symmetric cell is. So you have to put the metallic lithium same on both the sides, same interfacial layers on both the sides. First, you have to measure without interfacial layers what is the impedance pattern you are getting it. Then you have to measure perfectly putting these ones. Then what is the additional part you are getting it. Then you have to go for this circuit, this what you call fitting the circuits. And finally, you have to come to conclusions. How much is the contribution comes from the interfacials? Divide by 2. Really tough job, but one should have some expertise and experience and practice to help you to overcome this.
Okay. Okay, sir. Thank you, sir. Sir, one final question, sir. So what would be the typical thickness of the electrolyte, solid electrolyte, when we go for a bulk no fabrication part? If it is thin film, then it will be maybe some micron. But in the bulk fabrication technique, what would be the best electrolyte thickness for a high performance solid state battery, sir?
At present, say company industries are providing the one working with 3 industries. They are able to make it starting from 50 microns and 30 microns.
50. Mm-hmm.
So this 30 to 50 is the only thing. So if you increase the thickness, then there is no meaning in working with this solid electrolyte battery thickness. That's the advantage. With these oxides, you can make it very good shapes with size of the thickness of 15.
Yes, sir. Thank you so much for your informative and illuminating talk, sir, on this theme. Right. Thank you so much. We are grateful to you for your time. Right. So now the third speaker for this FTP is going to be Dr. I. Prakash. Dr. I. Prakash is an assistant professor from the School of Electrical and Electronics Engineering from Sastra University, Tanjavur. He did his postdoctoral studies in physics from Pondicherry University and PhD in physics again from Pondicherry University MPhil in physics from Pondicherry University, and his MSc and BSc studies were done from Madurai Kamaraj University. Dr. Prakash has 9 years of teaching experience, and presently 2 PhD candidates are going to submit their theses, and under his guidance 1 PhD got awarded and 2 PhDs are ongoing. His areas of research include nanocrystalline and nanocomposite electrode materials for lithium-ion battery application. And for today, he's going to deliver his lecture on pure and composite form silica aerogel, negative electrode for lithium-ion battery application. So I now request Dr. Prakash to take over the session. Thank you, sir.
So I'm Dr. I. Prakash. I'm going to deliver a lecture on pure and composite form of silica aerogel as negative electrode for lithium and battery application. I'm very thankful to Dr. Hari Prasad and the Associated Institute of Aeronautical Engineering, Hyderabad, for giving me this opportunity. And again, once again, I'm thankful to my professor, Professor N. Satyanarayana, as well as Professor R. for giving some basic introduction about batteries. So with this, I'm just entering into the topic. So why we need this energy storage devices? Because if you look at the non-renewable energy resources like petrol and diesel and even natural gases, so the pollution associated with the petrol and diesel engines causes enormous health issues. Apart from that, there is huge natural calamities effect. So you can see from the picture. So there will be a huge rain, and some places there will be a complete drying. So this will affect the nature. So in order to overcome this, we have to go for energy storage devices along with the renewable energy resources. So in the picture, it clearly shows the renewable energy sources like solar, wind, and hydro. But the only problem is they are not continuously available. So the sources are intermittent in nature. So what we have to do is we have to store the energy whenever the electricity is available from these resources, and later we can use it for our purpose. So for that, we need several energy storage devices. So if you look at this Ragoni plant, so it will clearly show why we have to go for lithium-ion batteries. So mostly Professor Murugan insight with the lithium metal and how we can overcome with the use of solid electrolytes. So due to the dendrite growth, even though lithium is suitable and having high gravimetric as well as volumetric energy density, but due to the safety issues, we have to go for lithium-ion batteries. So again, even if you consider the electric vehicle applications as well as portable and electronic devices applications, it is very much useful. And again, I'm just giving some brief introduction about the lithium-ion battery. So the lithium-ion batteries are powerhouse for all digital electronic revolution. So because of this high gravimetric as well as volumetric energy density, and so if you take any lithium-ion battery or electrochemical cells, it consists of 3 major components. So one is anode, and that is negative electrode, and cathode, that is positive electrode, along with the electrolyte. So there will be additional component, it is called physically avoid in contact. So it will avoid the contact of anode and the cathode, but it will allow the lithium ions to pass through in between the anode and cathode. So here it is first the lithium-ion battery is commercialized by Sony in 1991, and even then we are still require some more additional advantages, or we have to go through the incorporation of some changes so that we can avail high energy density. So even though the lithium-ion battery is having high energy density and no memory effect span, so modern lithium-ion battery requires high energy density as well as power density. So for that, we have to go for the next slide. What is the effect of high energy density and high power density? So in order to explain this, so I'm just giving some slides for water storage. So in the right hand side diagram, so the water can consist of different, it can have different capacity. So one is fine, it can occupy 500 ml water on 1 liter water or 2 liter water. So if I require so high water storage, then I have to choose the last one. So it will store more water inside. So this will reflect in the energy density or as well as the specific capacity of a material. So I'm just giving you an example. So carbon can store the lithium with the help of alloying reaction. So it will form LiC6. And it can store with the capacity of 372 milliampere hour per gram. So that means we can get 372 milliampere current from 1 gram of material for 1 hour. So that will reflect in the C rate. So 1 C rate, that is 1 C rate. Similarly, on the right hand side, if I want to draw water from the can, so if I put only one hole, so the water is coming out of the water bottle, but it will take longer time to drain. But in then additionally, if I put more number of holes, so instantaneously water from the bottle will come out quickly. So the power density reflects how fast I am going to take the charge from the stored material. So that is reflected in the charge rate. So 1 C rate or 0.1 C rate or 10 C rate. So here, whatever the charge stored in the material, I can draw the current. So with a different current rate. So for example, if it is a 0.1 C rate, then it will be 37.2 milliampere current I can draw for 10 hours. So I can work for longer time. But at the same time, if you are looking for high power applications like electrical vehicles, you need high current at short duration of time. But usually the battery is having high energy density, but having so in order to improve the battery performance, so one has to improve the power density of the lithium-ion battery. So that is the research mode. If the alternative is supercapacitor, but again the supercapacitors have high power density but low energy density. So in this lecture, I want to give some information about the anode material and how to improve the power density and what are the factors which will affect the power density. So in the coming slides, I am just giving what are the major components of electrochemical cells. So in the previous slides, I have explained anode, cathode, and the electrolyte are the major components, and along with that, separator. So whenever you are going to fabricate a battery, even your material is good enough, but during the fabrication time, you have to choose the proper separator and proper electrolyte and proper cathode and proper anode. Then only again the environmental conditions where you are going to assemble your lithium-ion battery in the glove box. That is also going to affect your battery performance. So if you take an anode material, so as explained by Professor Murugan, the lithium metal is having high capacity, but there will be a safety issues. Due to that, people are trying to switch over from other safe material like carbon. But the theoretical capacity of carbon is only 372 milliampere hour per gram. So in order to improve that, so researchers are trying to utilize different materials. For example, one example is silicon. Silicon can react with lithium through alloying and de-alloying reaction, and it can give 4,200 milliampere hour per gram specific capacity. But the major drawback of silicon is the alloying is more predominant than the de-alloying. That means during the alloying reaction, continuously your material is going to be deposited and it will not come back to the host material. So due to that volume expansion, so more than 300% volume expansion you can able to get in the silicon based material. So what is the problem with the alloying and the volume expansion? So one thing is your battery is going to bulge, and other one, if the alloying reaction continuously taking place, then there will be a mass accumulation in the material, and due to that there will be a local strain, and your electrode material may come back or come out of the current collector. So it will be reflected in the electrochemical impedance spectrum. So what is the alternate? So different metal oxides are introduced. So like copper, iron oxide, and binary metal oxides. So even SI wood. One has to look for alternative materials, and we should avoid this volume expansion, or how to improve the other performance. So that is the research point. Along with that, different cathode materials will be also used, and electrolyte. So as explained by Murugan sir, so whenever you are choosing the electrolyte, there will be option. So whether you are going for aqueous electrolytes or the lithium-based salts dissolved in water, or the lithium-based salts dissolved in organic solvents. So the difficulty in the case of aqueous electrolytes is the potential window. You cannot go beyond 1.2 volt. So unless otherwise you are adding some additives in it. So due to that, your restricted potential window is less. And in order to avoid or overcome this, the researchers are using the lithium-based salt dissolved in organic solvents. So again, if you want to increase the mobility, you have to increase the additives like propylene carbonate and ethylene carbonate. So in order to improve the stability as well as the mobility, so low viscous additives are added. Similarly, separator. Some separators, so with respect to lithium, so the dendrite can go into the separator and it will make a contact with the anode and cathode. So that will make a short circuit. So in order to avoid, so researchers are utilizing different kinds of separators. One is glass fiber separator. So it consists of more pores, so it can accommodate more electrolyte in it. So that is one more advantage. So whenever you are going to start research on electrochemical devices, you have to concentrate on any one of the material, either anode or cathode or electrolyte or separator. But while fabricating your battery, as well as while doing the performance, so even though your material is good, but sometimes your performance may be affected due to any one of the reasons. So the assembling time also, there will be some problem. So in the slides, we are going to discuss about the importance of porous electrode material. So already you are aware of that nano crystalline material or nano materials in the case of electrodes. So why we have to go for porous electrode material? So normally here I am just giving some example. So how the bulk material is appearing and how the porous material is appearing, sponge-like material. So if you look at this bulk material, so for example, if you are cut short this material into small pieces, but again it is bulk, there is no pores in it. But if it is in contact with the electrolyte, so it can contact only go over the surface. So the surface reaction is only limited by this bulk nature. But if you take a porous material, what will happen? Your electrolyte can enter into the material active material. So there will be a increment of your reaction. So percolation is increases, and accessibility of electrolyte with the electrode is also increases. And one more important product with the help of silicon. So if you take a silicon, so there will be a continuous volume expansion. So due to this, the bulging of electrochemical cell can happen. So now if you are using a porous material, so within the pores, the continuous alloying, even if alloying can take place, that will accommodate within the pores. So by this way, you can avoid capacity fading due to this continuous volume expansion. So here in the leftmost or left bottom corner, the graph shows the silica aerogel. So it's looked like a lightweight material consists of 99% of air. So only 1% of material. It is very, very light in nature and low density, high porous and high surface area. So using this kind of material as electrode, surely your accessibility with the electrolyte is improved. Also, your volume accommodation is improved, and the diffusion length is also decreases. So whenever if it is in contact with the electrolyte. And here I am going to concentrate only on anode materials or negative electrode materials. So the broad category, the anode materials are classified into 3 types. So based on the reaction type. So one is intercalation and deintercalation reactions. And the example is graphite and lithium titanium oxides, where the lithium is intercalate and deintercalate during the charge discharge reactions. The other type of reaction is conversion reaction. Here, the example, if you take a copper oxide or iron oxide or the ferrite system, if you take. So during the discharge, so it reacts with lithium and form lithium oxide. So as the reaction mechanism is given and it converts to metal. On further charging time, it is reversible. So the lithium oxide formed can decompose and the formed metal can convert to metal oxides. So this kind of reactions are known as conversion type of reaction. Apart from that, alloying and de-alloying reaction is also possible. So especially the material like silicon, germanium and tin. Here it can react with the lithium and form the alloy, and during the charge, so the formed alloy can decompose into the separate material. So again, it is a reversible reaction, but the reversibility is not equal. So that is the main problem in the case of alloying and de-alloying reaction. So when you are comparing this alloying, conversion and intercalation type and de-intercalation type of material will be more beneficial than others. And if you are taking a conversion reaction, so normally the potential it takes the discharge, it will be slightly higher than this intercalation and de-intercalation. But again, alloying and de-alloying, the electrode potential is still lower, so it will be useful for anode materials. And again, you can calculate how much charge it can store in a specific material with the formula. So here N is the number of electrons involved in the reaction. So in the beginning I told, so if LIC 6. So here for 6 carbon, 1 lithium is involved. But if you take silicon, so here LIX for 1 lithium, 1 silicon, so X number of lithium atoms are involved, so it will be higher. So surely your theoretical capacity, so if you are taking silicon, the theoretical capacity is around 4,200 milliampere hour per gram. So that means if you have 1 gram of silicon, you can take 4,200 milliampere current for 1 hour. So this is the nature for silicon. But I already explained what is the problem in the lithium silicon based anode material because of its continuous alloying reaction. So the de-alloying is less, and the volume accumulation will be more. So one has to go for different kinds of materials. So other materials like graphite and copper oxide and silicon and silicon. So here the theoretical capacity can vary. So if I want to use different electrode materials, one, I have to increase the energy density that depends upon the theoretical capacity, and one more is the power density that depends upon the porosity or how the electrolyte is going to react with your electrode. So based on that, so in order to overcome this alloying problem, so I have chosen silicon with an appreciable theoretical capacity of 1962 milliampere hour per gram. But it is surely less than silicon, but we can utilize that. So in the broad category, I have chosen the silica as an anode material for lithium and batteries. And in order to improve electrochemical performance, I just increased ferrites. So 10% of spinel ferrites are added together and increase the performance. Along with that, include or I can incorporate Li2O as additional material. So because if you take the conversion type of reaction material, so during the discharge, Li2O will be formed and it will be decomposed and it react with the metal and it will form the corresponding metal oxide. So additionally, I have incorporated Li2O in the source material. So the advantage of this incorporating Li2O is, one is I can improve the ionic conductivity, and the other one I can improve the number of charge carriers in the material. So in this aspects, again, I have confined the research topic into some 3 categories. So here I am going to prepare silica aerogel, and I have to tune the surface area and porosity. And the other one, I have to incorporate Li2O as well as the ferrites material in the silica aerogel so that I can improve the performance of the material or performance of the battery. And third one is again the similar one, incorporating Li2O along with that nickel ferrite in the silica aerogel. Even though it looked like similar, so in the first one, I have studied about the fine tuning of surface area and porosity and its effect on lithium storage performance. Second one, additive effect. So one is ion conducting additive, that is Li2O, and electron conducting additive, that is super P carbon during the electrode synthesis. So that effect is studied in the second part of work. And that part of work, how the fading mechanism is arises. So that also I have studied in the third part. So first one, I will explain that surface area tuning as well as porosity of SiO2 aerogel. So before going into that, so first I have to introduce the concept of aerogel. So SiO2 aerogel discovered by Whistler in 1931. So here, if you consider a silica aerogel, it can be considered as a frozen smoke. So if you see the smoke, the air molecules, again, it is in the form of colloids. And if you frozen it, you can able to get a lightweight material or low dense material. This kind of low dense material is known as aerogels. So again, aerogels consist of 99% of air trapped inside the material and only 1% of material is your skeletal network. And again, what is the advantage of your aerogel is it's having high specific surface area and low density as well as low thermal conductivity. So based on that, there are plenty of applications for silica aerogel. Since it is thermal insulation, it won't conduct temperature or the thermal conduction. And cosmic dust capture. And since it is having the high surface area and porosity, It can be used in the water purifier, and apart from that, it will be also used as a energy storage devices and dye removal and plenty of applications. So here I'm checking for energy storage devices because of its high specific surface area and high porosity, which will enhance the electrolyte circulation, as well as it can accommodate more number of lithium ions. So these graphs will tell the importance of your silica aerogel. So first photograph showing that the overcoat, so made of your silica aerogel. Since it is a poor thermal conductor, so very cold places you can wear it to avoid the low temperature. Similarly, the second is the dust collector in the space, and again it is a poor thermal conductor, so it can be used as a tiles for making outside this spaceship. So once it is entering into the atmosphere, so due to the friction, high temperature can cause the collapse of this spaceship. In order to avoid that, so outer surfaces, the tiles are made up of your aerogels, so it can withstand high temperature. So since it is 99% of air is trapped inside, so it is a poor thermal conductor. Apart from that, it will also useful for effluent removal. So either dye removal. That purpose also we can utilize the aerogels. So here the aerogels can be prepared in different kinds, whether it is a freeze drying or surface modification or supercritical drying. First of all, here I am using the supercritical drying method. So we have to know what is a supercritical drying. So for that, we need to know what is a supercritical fluids. So for example, so certain liquids are exhibit the supercritical nature. For example, carbon dioxide, water, methanol, ethanol, acetone. Apart from that, again, list is there, but I am giving just a few examples. So if I increase the temperature of this particular solvent, for example, if I keep ethanol in the vessel and slowly increase the temperature, and once it increases temperature, during that time, the inbuilt pressure is also increases. Once it crosses the critical temperature and critical pressure, so in the phase diagram you can see, so this is solid state, this is gaseous state, this is the liquid state. Once it crosses the supercritical state, even though, for example, if it is a ethanol in the liquid state, it will behave like both gaseous as well as liquid state. That is the advantage of supercritical fluid. At the supercritical fluid stage, it can dissolve salts as well as it can escape like a gas. So now I will tell why we have to take this fluid to the supercritical stage. For example, if I have the silica matrix and filled with ethanol, by taking the ethanol to the supercritical stage without crossing the boundary, so I just reach the supercritical stage and slowly evaporating. So the ethanol present in the material will come out like a gas. So it will not affect the volume. So it will not affect the volume. So completely the ethanol removal is possible from the vessel. Then after that, your vessel temperature is slowly come down to room temperature. So these are all the following supercritical liquids here we are using. So I have used ethanol as a supercritical liquid to dry the silica alcohol. So in the diagram, so this is the photograph images of for autoclave. It consists of the pressure gauge along with the inlet valve as well as outlet valve and the furnace setup. It is controlled by the temperature control. So inside we can have the glass liner. So here the alcohol. So I will come into the next slides. So what is the meaning of alcohol? Alcohol is kept and half of the ethanol is filled. So once the temperature ramp is set, your temperature is gradually increases and also the pressure is also increases. Once at the temperature of 241 degrees centigrade, your pressure, if you measure with the gauge, it will be 60.6 bar. So slightly, if you increase further, your pressure is going to increase. So that is the supercritical stage. That time, your material will not shrink since it is the liquid is in the supercritical stage. With outlet valve, you can release the ethanol vapor. Once it is completely evaporated by maintaining the same temperature, then gradually you can take it to the room temperature. If you take out of the sample, it will be in the form of aerosol. So it's having high surface area and porosity. So this is slides represents the steps involved in the soldier process. So first, if you take the preparation of aerogel, it consists of two steps. One is formation of alcohol and conversion of alcohol to aerogel. So here in this diagram, so it will give the dense solution. So dense ceramics can be prepared. So here what will happen? So first the precursor chemicals is alkoxide, tetraethoxyarthosilane is added with the water. Since it is not visible, so we have to continue the hydrolysis reaction. So we have to take the common solvent as ethanol. With the help of ethanol, both TOS as well as water will mix together. Again, it will be turbid nature. So we have to add catalyst. So if you are adding acid catalyst, the growth will be in the fibrous type. If you are adding base catalyst, the particle growth will be there. And continuous reaction will give byproduct of water as well as ethanol. That will be kept in the force network. Up to this is common for so what you have to do, you have to dry it in the oven. So what will happen? The pore diameter is going to decrease and the inside pore, whatever water or ethanol will come out. So the complete monolithic form will be collapsed. And finally, you can make it in the form of a dense ceramic. Here in the form of aerogel, so we have to take in the wet gel. And what you have to do is, you have to keep it for solvent exchange. Solvent exchange is here in the alcohol gel, the pores consist of water as well as ethanol. Now, dry nitrogen gas through this. And we have found that the aerogel exhibit hydrophobicity. So in order to study very clearly, so we have made some 4 categories. So first one, S1, without purging carrier nitrogen gas. So the sample aerogel, silica aerogel is prepared without purging nitrogen gas. Second one is continuous flow of nitrogen gas for 60 minutes. This is after releasing the ethanol vapor at 255 degrees centigrade. So at 255 degrees centigrade, you have to purge the nitrogen gas and it will be constant continuous flow for 60 minutes. And S3, here after removal of the ethanol vapor, now you have to send 10 bar nitrogen. So you pressurize the vessel with the 10 bar nitrogen gas and it will be kept for 30 minutes. Then it will be released, slowly released, and the temperature has come down to room temperature. The fourth one is 20 bar nitrogen gas is pressurized in the vessel and later it is slowly removed. So even though it looked like similar, but it is affecting the porosity as well as surface area. So this porosity and surface area is going to change the battery performance. That how it is going to affect, that we will see in the following slides. So in the hydrolysis, the TOS react with water and form the continuous chain network with the release of either ethanol or water as a byproduct. And this graph shows the phase diagram, how your ethanol is going to supercritical state, and second one slowly releasing the ethanol vapor by maintaining the temperature. We can maintain the monolithicity of your aerogel, and finally the nitrogen budging. So accordingly, we have 4 samples: S1 without nitrogen budging, S2 continuous nitrogen flow for 16 minutes, S3 10 bar nitrogen at 255 degrees centigrade for 30 minutes, then it is released, and S4 20 bar nitrogen at 255 degrees centigrade for 30 minutes and slowly released. So in order to explain what is the effect of nitrogen budging, so once the silica aerogel is formed within the ethanol vapor, and again it is 255 degrees centigrade. So even though it is in the supercritical state, it will behave like both a fluid as well as, that is liquid as well as gas. It can interact on the surface. So partially it can eject the OH groups as well as the ethanol groups which is present in the surface. So that will create defects. And whenever we are introducing the nitrogen gas, again it will be at 255 degrees centigrade. What it is going to change is, it is going to affect the surface. Again, it can eject more number of OH groups and more number of CH3 groups. It will form more defects than the without nitrogen budging. And apart from that, once you are introducing nitrogen gas inside the vessel, so there will be a pressure. So it will affect the morphology. So the pore size is going to decrease, as well as the surfaces, the particle nature is changed to like layered. So there will be a compression at 255 degrees centigrade. Along with that, there may be a possibility of slightly carbonized organics presence with the help of nitrogen budging. So these are all the expectations. So we have to prove what is the effect of nitrogen budging with the help of different characterization techniques. So for that, we have utilized, one is water contact angle. So without nitrogen budging, the prepared silica aerogel exhibits hydrophilic nature. So with a contact angle of 79 degree. But if you look at that, the contact angle is gradually increased. So 110 degrees centigrade for S2 sample and 139 degrees for S3 and 142.3 degree for S4 sample. So the contact angle is going to increase and it slowly move towards the superhydrophobicity. So what is the origin of this hydrophobicity increment? So in the earlier previous slide, I told that there will be a collision of nitrogen molecule with the silica aerogel. So it will eject some of the reactive, surface reactive OH as well as ethanol groups from the aerogel. So it will create more number of defects. So due to that, the water contact angle is increases. So if I make a drop over the silica surface, silica aerogel surface, if there is no water reactive groups on the surface, surely your hydrophobicity is going to increase. Along with that, if there is more number of defects on the sample, that it will be reflected in the water contact angle. So this is one observation. So we have to prove. So for that, we have taken the FTR analysis. So in the FTR analysis, S1, S2, S3, S4 samples. So we guess S1 sample may consist of more number of OH groups. So that is clearly observed in the region between 3800 to 3000. Along with that SaOH groups, That is also more predominant in the case of S1 sample. So that reflect that since without nitrogen, some partial OH groups is present, that will reflect in the water conductivity studies. Also, if you look at the S4, so few OH groups are present. That is also reflected in the water conductivity. So what we have to go further. So we have taken the nitrogen adsorption, desorption, isotherm measurements for all the 4 samples. And the results exhibits, so the S1 sample giving 540.2 meters square per gram. That is the surface area of the material is 540. And if you look at S2, it is 689. It is increased. And S3, it is 576. And S4 again 638 meters square per gram. If I blindly take, so S4 sample, for example, this material is having high surface area. So high surface area is essential for the electrode reactions. On the basis, if I select either S4 or S2, I may end up with the different answers. So we have to analyze what are the other observations along with the surface area. So if you look at this pore diameter distribution, in the S1 sample, the average pore diameter is in the region that is mesoporous. So 2 to 50 nanometer according to AICTE classification. The pore diameter it is 2 to 50 nanometers comes under the category of mesoporous. If it is less than 2 nanometer, it is microporous, and greater than 50 nanometer, it is macroporous. So for S1 sample, majority of the pores are mesoporous. But whenever we are introducing the nitrogen, so due to the pressure, so some of the mesopores turns to microporous. That is reflected in the pore volume. So here for S1 sample, the pore volume will be higher than this S2 and S3 and S4. That result is also reflected here. So S1 sample surface area, even though it is 540, the average pore size is 25.3 nanometer. And for S2 sample, the average pore size is 18.6, S3 it is 20.9, and S4 it is 20.7. So among all, S1 sample is showing high porous size. And similarly, the pore volume, if you look at that, S1 sample is having more pore volume compared to the rest. So with that, we have chosen 2 material for testing purpose. So S1 as well as S4 for battery fabrication. So because even though it is having so a slightly lower surface area, but the pore size is more and pore volume will be more. And we have also tested the thermal behavior with the help of TGDTA. What we can expect is, since without nitrogen purging, so there will be a OH group is present in the material. That is reflected in the FDR results. Similarly, the same results we can expect in the TGDTA. There are 2 regions have marked. One is region 1 and region 2. So S1 is without purging sample. S4 is 20 bar nitrogen gas is purged. So it will take out more number of OH groups. So in the beginning, so the temperature near 100 degrees centigrade, whatever the weight losses correspond to the evaporation of OH molecules. So if you see the weight loss, it is 20.59% for S1 sample. For S4 sample, it is 15.94%. So there will be a less number of OH groups present in the S4 sample. That is also reflected here. And second weight losses in the region between 400 to 600 degrees centigrade. That is due to the decomposition of organic residuals. So here without nitrogen purging, so organic residuals are less in number. But if you are looking at the S4 sample, so due to the nitrogen purging, there will be a formation of carbonized compound. So that carbonized compound is decomposed at this region. So the weight loss will be compared to S4. So 32.69, here it is 29.66. and both the samples exhibit amorphous nature. So here region 1 endothermic, one is 62 degrees centigrade, and region 2 it is 450 to 470 degrees centigrade. Again, we have looked at with the help of electron microscopic images and TEM SED pattern. So S1 sample exhibit clearly particles over the surface, and S4 sample, due to the applied pressure, a layer formation. So instead of individual particles, it will form a layer, and additionally the pores are compressed in it. And here, with the help of 10 images, you can able to see the pore size. In the, again, it is similar to your red surface area, pore diameter. So it is in the range of 25 nanometer, which comes under the category of mesoporous material. And again, SEAD, selected area electron diffraction images also. So diffuse pattern that reflects the amorphous nature. So along with that, we have taken the XPS analysis. XPS survey scan reflects the presence of carbon with a percentage of 12.28 in the S4 sample, and S1 it is 8.63. So there will be an increased carbon content. That may be due to the nitrogen purging effect. So carbonization can be improved. That is also reflected in the TGDTA weight loss. And we have also taken the pore spectra and deconvert it with the help of standard available with the literature. So here in the black color representation is for your S1 sample, and red color representation is for S4 sample. And if you look at that, SiOH groups as well as carbon, and it is attached with the SiO2 is also attached with the carbon and oxygen. So that will give much information about the bonding of Si with the different materials. So whatever we have observed in the FTER as well as TGDTA thermogram analysis, that is also supporting. XPS analysis also supporting this evidence. And the nitrogen one is, it can clearly evident that the nitrogen is not bonded with the silica aerosol. There is no appreciable band. So which is clearly evident that nitrogen is not incorporated in the material. It is just like a carrier gas. So the role of nitrogen is only a carrier gas. It will take out moisture as well as the ethanol vapor from the aerosol surface. And later we are going to fabricate the lithium-ion cell assembly. So here we have taken the slurry preparation. So in the beginning, I have told the advantage of high surface area as well as high porosity material, but there will be a disadvantage. So we have observed. So while we are preparing the active material, first initially we have started with the low binder ratio. So here we have utilized 60% of active material and 20% of carbon and 20% of binder. So if you are decreasing the binder ratio, so the material is not sticking with the current collector. So that is due to the high surface area. So for that only we have increased the active material current binder as well as this carbon black ratio. So here active material is silica aerosol, S1 and S4, and super P carbon is act as a conducting additive, electronic conducting additive, binder and solvent. We have used two kinds of binder. One is sodium alginate, it is water soluble. Other one is PVDF. So two binders. So here in the case of aerosol material, so sodium alginate is not a very good binder because of its high surface area. So it is not sticky with the current collector. So we have utilized PVDF as a binder for this studies. For rest of the studies, the composite material, we have utilized sodium alginate. And in the electrode coating process, the current collector, that is 9 micron thick copper foil we have taken. Coating thickness is around 10 mm thickness with the help of auto electrode coater, and it is dried in vacuum at 110 degrees centigrade for 12 hours, and we have tailored the electrode disc in the diameter of the we have made, and we have assembled the cell in the argon filled glove box with the help of Pondicherry University Professor Satyanarayana sir laboratory. So here the electrolyte we have used is 1 molar LiPF6 in propylene carbonate and ethylene carbonate in the equal volume ratio. That is commercial electrolyte we have used. Separator we have used glassy microfiber obtained from sigma altitude, and counter electrode, that is lithium metal, and it is assembled in the Swagelok cell, and we got the open circuit voltages 2.71 voltage. And later we have tested the battery cycle performance with the help of Biologic ECS 810 battery life cycle tester. And here it is S1 and S4 sample. So first initial discharge, it represents 2 major peaks, and again lithium silicon alloying. So 1 and 2 involves this irreversible solid electrolyte formation along with the reaction of electrolyte with electrode, and 3 is correspond to your alloying reaction, and 4 is correspond to de-alloying reaction, and 5 is correspond to this additional reaction, that is SaO2 is react with the lithium and form Li2Si2O5, and these are the reactions we have observed with the help of cyclic voltagram. So the initial observed reduction peaks are absent in the subsequent cycles. So again, if you look at that, the alloying, de-alloying, as well as the reaction with the SaO2 with the lithium is observed in the following cycles. And later we have gone for cycle life studies. We have tested up to 100 cycles, and the initial discharge capacity is higher for S1 sample. For S4 sample it is lower, but even then we can able to get a stable performance. Even though the theoretical capacity of the SaO2 is larger, but we could be able to get a stable performance with the help of SaO2 electrodes. So that is observed, and we have also tested the electrochemical impedance before cycling as well as after cycling. So here we could be able to see that is S4 sample after cycle. So here this after cycle the resistance is increases, but in the case of S1 sample the electrochemical impedance is decreases after cycle. That is reflected in the next graph. So it is after cycle, after 100 cycle, we have again taken the CV measurement. So for both the samples, S4 sample does not exhibit well defined alloying and de-alloying reaction. So, but in the case of S1 sample, it exhibits both alloying and de-alloying reaction. So even after 100 cycles, it exhibits. That means whatever the available surface area, even though it is low, but the pore sizes in the mesoporous range compared to S4 sample. So whatever the accommodation, volume accommodation, it will not affect the reaction. So even after 100 cycles, the alloying and de-alloying is predominant, and so that contribution is stabilized and it is observed for even 100 cycles at 100 milliampere per gram current density. So with this, we can able to conclude that. So we have prepared SaO2 aerogels. So initially our aim was to improve the surface area and porosity. At the end, we could found that not only surface area, your pore size is also dominant in the battery performance. So we could able to get 95% of coulombic efficiency, and again further research is going on to incorporate in situ carbon in the SaO2 aerogel, and that is published in the Applied Surface Science Journal in the year 2019. And next work, I'm going to give the Li2O and copper ferrite incorporation in the SaO2 aerogel. In the case of Li2O as well as copper ferrite, so the following ratio is taken: 10% of copper ferrite in the 90% of SaO2 aerogel, and again the La2O ratio is increased 1, 2, 4, 5% by decreasing the rest of the compound percentage to 98, 97. And here again we are varying the copper ferrite ratio, and the synthesis is similar to our earlier synthesis. The only difference is after hydrolysis with the TOS and water, we are adding the precursor chemicals corresponding to ferrites as well as the lithium oxides. So the lithium nitrate is a precursor for Li2O, and for respective ferrites, the corresponding nitrates is taken. For example, if it is a copper nitrate and iron nitrates are taken in the respective stoichiometry ratio in the solution form. And finally, we got the alcohol. Here, solvent exchange process is not done. Directly, we have taken the alcohol into the autoclave with the half-filled ethanol, and we performed the supercritical drying. But compared to your pure SaO2 aerogel, we are getting pieces of aerosols. Here, we are not getting monolithic form of aerogel, because in the case of SaO2 aerogel, this bond is broken easily, though, so you will get the broken pieces. And in the next slide, we are going to show the X-ray, powder X-ray diffraction pattern as well as the FTIR spectrum. So, since the quantity of copper ferrite is very, very low, we could not able to get the complete formation of copper ferrite in all the rest of the samples except for composition. But we may get the expected copper ferrite phase if you are increasing the temperature. But we have to compromise to the surface area as well as porosity. If you are increasing, surely the porosity as well as surface area is going to decrease. So you have stopped at such 255 degrees centigrade as a final temperature. And here we could be able to see the formation of copper metallic peaks along with the copper ferrites. So there will be a mixed phase formation, Fe2O3 and copper ferrite as well as copper metallic phase. And that is reflected in the FTR spectrum. And we could be able to see SaO, SA, asymmetric stretching and symmetric stretching, and SaOH bond formation along with the metal oxides formation. Then this powders, dried powders, are made in the form of pellet and surface coated with graphite. And we have measured the AC impedance analysis for the pellet samples. And we have calculated the conductivity with the formula. Thickness of the pellet we have measured, and from the fitting parameter we could get the bulk resistance, and from the area we could be able to get the conductivity resistance. In that, we could observe that 5% of Li2 added copper ferrite SaO2 aerogel is exhibiting high conducting nature, even though it is showing the order of 2.4 into 10 power minus 9 Simon centimeter inverse. So the problem with the SaO2 aerogel, even though it is having high surface area and high porosity, it is non-conducting nature. So we have to increase the conductivity. For that purpose, we have included Li2O. So later we have also included the conducting carbon additive improvement during the electrode preparation. And this is the same images. It could clearly show the formation of particles of nano in size, and similarly the TEM images also reflecting that SaO2 matrix. Within that SaO2 matrix, your copper ferrite is formed. Then we have gone for the N2 adsorption desorption analysis. It clearly shows the decrement of surface area. So earlier it is above 500, but here the surface area is enormously decreased to 60.4 meters per gram. and also cumulative pore volume as well as pore area is increases. And with this, again, we have got XPS elemental analysis. We could be able to observe presence of elements like silicon, iron, and copper and lithium. We have taken the pore spectra and deconverted it. We could be able to see the presence of Fe3 plus as well as Fe2 plus and SaO, Si as well as SaO's carbon, the bonding, as well as the presence of Cu2 plus and Li2O formation in the particular aerogel composite. And again, in the electrode preparation, we have taken two ratios. So one is active material is your 70, 20, 10. So one is 70% of active material and 20% of super P carbon and 10% of sodium alginate binder. So sodium alginate is a binder, that is a water soluble binder. It will be more suitable for a silica based material, but the only drawback is here we could show the high surface area. That's the reason why we could not able to utilize the sodium alginate as a binder. So we have used sodium alginate binder here because the surface area reduces. So one more sample we have taken, reducing the active material ratio to 40% and conductive additive is 50% and binder is 10%. So here we have taken the same kind of electrode coating process, and finally we could be able to see the cyclic voltammogram results of the three samples. So first one, the reaction is, and 2 and 3 and 4 are the following reactions. It involves both SaO2 as well as copper ferrite. So in the beginning I told that copper ferrite involves the reaction with the conversion of copper as well as iron with the formation of Li2O at the initial cycles, conversion reaction taking place. And along with that SaO2, we could be able to see the allying de-allying reactions. So for the second sample, that is 5%, that is without adding lithium. So the first one is without addition of lithium, Li2O, that is pure copper ferrite incorporated silica with the 20% of super P carbon. And second one is 5% of Li2O added copper ferrite SaO2 aerogel with the 20% of super P carbon. Now if you compare and we have normalized, that is current density, here the current density increases with the incorporation of Li2O. So that means the incorporation of Li2O enhances the ionic contribution. So that is reflected in the CV charge discharge pattern. And third one is 50% of super P carbon is incorporated. And here you can able to see clearly the alloying and de-alloying along with the conversion reaction is increased. But most of the places, so one doubt may arise. So what is the contribution of super P carbon? So that is we have analyzed in the next work. We have also taken the cycled electrode XPS. In that we could not able to see any formation of lithium with the carbon. That prove that here the super P carbon is not involved in the allying de-allying reactions. Only the silicon is involved in the allying de-allying reaction. So that is predominant. So whenever we are incorporating the Li2O, its performance is going to increase. Now, if you are increasing the super P carbon in the aerogel composite, again the current density increases. That is reflected in the charge discharge studies. So here, copper ferrite, pure copper ferrite loaded SaO2 aerogel and 5% of Li2O loaded copper ferrite aerogel with the 20% of super P carbon and 5% of lithium oxide incorporated copper ferrite aerogel with the 50% of super P carbon. So if you look at this analysis, the discharge capacity is higher in 5% of Li2O incorporated with the 50% of super P carbon. So what is the inference we got from this results is not only ionic conductivity. So the electronic conductivity improve the battery performance. So that is reflected in the cycled CV for 5% of Li2O loaded copper ferrite SiO2 aerogel. So with this, we are giving the summary of the second work is we have analyzed copper ferrite loaded SiO2 aerogel with 20% of carbon and 5% of Li2O loaded copper ferrite SiO2 aerogel with 20% of carbon and 5% of Li2O loaded copper ferrite SiO2 aerogel with 50% of super P carbon. So in that, the last one exhibit initial discharge capacity is higher and capacity improvement as well as coulombic efficiency is also better compared to the rest of the two. So from this studies, we could able to conclude that not only ion contribution, we also need electronic contribution. So in the first work, we could able to tell not only the surface area, the pore size is very, very important. So again, it looked like similar. So Li2O added nickel ferrite SiO2 aerogel. So the same preparation method we have followed for this also. And we have analyzed the sample with the help of outer X-ray diffraction as well as the FTR analysis. Here we could not able to see the clear formation of nickel ferrite because the quantity of nickel ferrite is very, very low compared to SiO2 and it is well formed well within the amorphous matrix. So if you want to get the nickel ferrite phase, we have to increase the temperature. So we have don't want to reduce the surface area as well as the porosity. So for that purpose, we retain that sample and the observation is clearly visible, whatever the Li2O formation as well as the ferrite formation is also visible in the FTR analysis. Then we have taken the impedance spectroscopy for the pellet samples. So again, the same procedure we have followed. So for without Li2 added sample as well as 1%, 2%, 5% added sample. So we could able to get high conductivity. So here the conductivity is a combination of both. Electron contribution will be there as well as ion contribution. Since most of the ferrite system, the contribution is hooping conduction. And so that is reflected here. And we have taken the SEM images for both the samples. So that is 5% of Li2O loaded nickel ferrite SiO2 aerogel. It's look like skeletal network. So the formation of skeletal network is observed. And here also from TEM images, you could able to see the formation of tiny particles of nickel ferrite. It is formed well within the SiO2 matrix. Since it is formed well within the matrix, we could not able to detect sufficient X-ray diffraction patterns from the sample. And we have taken the N2 adsorption, desorption isotherm. And from that, wet surface area is slightly improved to 116 meters square per gram. And cumulative pore volume, cumulative pore area is also represented here, 0.9 centimeter cube per gram and 99 meters square per gram. And finally, we have taken the XPS analysis for the sample, a synthesized sample that is taken at 255 degrees centigrade. And it clearly shows the presence of surface spectrum, clearly show the presence of nickel, iron, as well as silicon, the carbon and oxygen and Li. So the core spectrum is deconvoluted and it clearly give the formation. Si is formed with the oxygen bonded with oxygen as well as carbon, and Fe is retained as 3+ state, and copper is retained as in the Na2+ state, and the lithium is formed as a Li2. And we have gone for the charge discharge analysis as well as CP. So that is, we have taken 50% of super P carbon sample and 20% of super P carbon added sample and without added Li2O sample. So in that, we could able to see the better performances of your 5% of La2 added nickel ferrite SiO2 sample with the 50% of superbig carbon. And again, cycled electrode is also that here the alloying and de-alloying reaction is not observed. So only the conversion reaction correspond to nickel ferrite is observed. And we could able to see the Coulombic efficiency for 96.6% for nickel ferrite loaded SiO2 aerosol and 98% for 5% of La2O loaded nickel ferrite SiO2 aerosol with 20% of superbig carbon and 98% of Coulombic efficiency for 5% of La2O nickel ferrite SiO2 aerosol. So again, we have not leave it as such. So what may be the reason behind this capacity fading? So for that purpose, we have gone for cycled electrode analysis. So for cycled electrode analysis, we have taken the XPS measurement as well as SEM images. We have taken the fresh electrode and we have two cycled electrodes. One is after the end of charge, that is after reaching 3 volt, we have disassembled the cell in the glove box and taken the electrode. Other one is at the end of discharge and 0.005 volt. Then this cell is disassembled in the glove box and it is washed with the electrolyte solution and kept in the desiccator, and we have taken the XPS measurement and we have reached the surface with a 5 nanometer, and we could able to see the analysis results for pristine electrode and at the end of charge, whatever the electrode, and at the end of discharge. So by comparing this, you could able to see the SiO2, it is slightly shifted. So that is associated with the reaction formalism. So at the end of discharge, we could able to see Li lithium is bonded with LiXOY as well as LiSi. The alloying reaction is confirmed. So nowhere it is not reacting with the carbon. So that is proved that carbon is not involved in the alloying reaction. At the end of discharge, we could able to see the de-alloying. So the LiSi is not absent, not present. So we could able to see the formation of LiXSiOy. So it is not completely reversible. Similarly, with the help of Li1s spectrum, so Li2O is observed in the pristine electrode, and Li2O, Li4SiO4, and LiSi is bonded. So that will give the additional information of the electrode reaction. At end of charge, we could able to see Li2O formation along with Li4SiO4. So here again, the alloying is completely removed at the case of end of charge, but La2O as well as La4SiO4 is present in the material. So that is not completely reversible. So with the help of nickel and iron, so if you look at the pristine electrode, it is in the Na2 plus state as well as Fe3 plus state. At the end of discharge, so Na2 plus is converted to Na0 and Fe0, that is in the metallic state. Again, at the end of charge, we could able to see Na2 plus, Fe3 plus along with the presence of metallic state of nickel and iron. So what is the inference? So even though we have charged first cycle and then after charging, it is not completely reversible. It is not completely reversible. So that is resulted in the fading mechanism. That is resulted in the fading mechanism. So we have also tested the pristine electrode after first end of discharge, after first end of charge. So the SEM images also clearly shows the crack formation. Along with that, we have also calculated the lithium diffusion coefficient. So for all the and we could able to see pristine electrode, it is in the range of 10 power minus 14, and first discharge, it is increased, that is due to the alloying formation, and first charge, it is decreased, that is due to the formation of oxides. At the end of 10th discharge, it is further decreased. So from these results, we could be able to see the fading mechanism. So here, even though we have utilized 50% super P carbon and 5% of La2O, we could able to see that is a partial conversion here, Na0 to Na2 plus and Fe0 to Fe3. Perfect. So that is observed in the case of XPS analysis. With this, we could able to improve further. We could able to improve by incorporating the additional carbon. So here, whatever we are added is external super P carbon during the electrode preparation. So by one way we can improve all the performances. We can incorporate carbon additives during the synthesis time, and we can carbonize under the nitrogen environment. And second one, also in the composites, we can increase the temperature so that we could be able to form the crystalline formation, and also we could be able to increase the performance by incorporating the additives. So with this, we are come to an end of the presentation. So these are all the publications obtained from this work, and these are all the list of equipments available in our laboratory. And this is the paper, that is nitrogen gas interaction on silica aerogel, effects on hydrophobicity, surface area and porosity, and lithium ion battery performances, published in Applied Surface Science in the year 2019. And ion and electron conducting additive effect on lithium ion charge storage performance of copper ferrite SaO2 composite aerogel anodes, published in the Ceramic International in the year 2020. And capacity fading mechanism of La2O loaded nickel ferrite SaO2 aerogel anode for lithium ion battery XC2 XPS analysis is published in the journal Applied Surface Science in the year 2021. And I would like to thank Sastra Deemed University for supporting the research facilities, as well as SERP for giving funding opportunities for carrying out this research work. Also, I thank my PhD students for helping me to get this results. With this, I come to an end of this session. Now, Hariprasad.
Yes, sir. So thank you so much for your copious and informational lecture on pure gel, that is silicon aerogel. Thank you, sir. And now it is open for the questions that you have it on your mind. You can just please raise your hands, or else you can post in the questions. Anything is fine. So welcome back to the afternoon session. Dear participants, good afternoon once again, and welcome back to this 5-day ETAL faculty development program on energy storage. So let us start the third session. That is, the third speaker's talk will be given in a few minutes. So prior to that, I would like to introduce Dr. Venkateshwarlu sir. Dr. Venkateshwarlu sir is currently head research and development of the lithium-ion batteries at Amara Raja Batteries Limited, and has a vast research experience in the field of materials and battery technologies. Dr. Venkateshwarlu did his postdoctoral research on lithium-ion batteries at Taiwan University of Science and Technology. And before that, he served as a faculty at SRM Ishwari Engineering College and was first faculty to receive the research grants to develop solid electrolytes for solid-state batteries. He has a strong passion on creative research and is also a co-author of 100+ research articles. He is one of the members of IGSTC research project and Amara Raja India in India. And also, he served as BOS member of Pondicherry University, and also Yogi Vemana University, Vignan University, GVP Engineering College, and CR Engineering College, and also a life member in SAEST, KECA, and QCFI Tirupati. And talking about his contribution to research, He has contributed to several electrochemical power source events and organized international conferences on sustainable energy storage technologies for smart cities in association with IIT Tirupati in 2016 and, and SRM University AP in 2018. And now I invited Dr. Venkateshwarlu to give his valuable lecture on materials perspective for lead acid battery applications. Sir, Venkateshwarlu sir, please take over the session. Thank you.
Yeah, thank you, ma'am, for your kind introduction. So I will thank you very much for giving this opportunity to present both the technology, whether it's a battery lead acid or lithium ion. Maybe tomorrow we'll have a session on lithium ion. And I will share my screen.
Yes, sir, you can. Yes, it is visible, sir.
Visible?
It's visible.
You want in the presentation mode? It's good enough. Okay.
Yes, you can maximize it if you want. Otherwise, yes.
Yeah. Thank
Yes,
you
sir,
very
it's
much, ma'am.
perfect.
Once again, thank you very much for your kind introduction, and also thanks to Dr. Hari for giving this opportunity to share the battery and its importance. As you all aware of that, maybe morning this yesterday and today morning also you may having various sessions on the materials. There is a lot of interest on the batteries today because of a lot of greenhouse gas emissions. Maybe it is due to the industry, maybe due to automobiles, maybe due to any other reasons. That's the waste, landfilling of some of the toxic chemicals. All these things contributes to the this greenhouse gas emissions, and it affects our life and also impact on the environmental as well as quality of air. So yes, lead acid battery. This today topic will cover about the material prospect of lead acid batteries. And lead acid battery is, I can say, it's one of the most promising battery in the secondary or rechargeable batteries. The reason is because this is just now it is completed 60 years. It was invented by Glaston Plantain in the year 1859. So almost 160 years old technology. Still, it is competing with the young generation, that is new energy storage technology or the battery technology like lithium or sodium or any other metal air batteries. The reason is this has, though it has some disadvantages, but more advantages to us. You can look at that if you want to have you want to switch on the TV, you need to have a remote, you need to have a battery. It is a primary battery or a secondary battery, whatever it may be. Similarly, you want to drive your two-wheeler, again, you need to have a battery. That is a start of the vehicle. So like that, so if it is, that is a small scale, but when you go for this bigger scale, that is a gigawatt scales or the ESS, that today we call it as earlier we used to tell that's a backup for solar, and today we talk about the energy storage solutions for the megawatt to gigawatt hours. So when lithium came and people have started using a mega to the gigawatt. So then straight I will go to that. We'll see the with that few words about the batteries and its importance in the automotive sector and also industrial segments. Like the most important I have not touched upon. That's the if you are talking to the people or we are watching this live uh, presentation, it's all due to the effective communication, effective internet communication. So internet, if you want to have a it is a signal from the towers, you need to have a battery backup. So our battery is very important, and it is a part of our life, I can say that. whether it's a mobile or it is something else or it's household home appliances. So I just broadly just grand challenges and energy storage technologies. Just I'll see the market trends and lead acid batteries and see the electrochemistry, how this advanced lead acid batteries compete with that. What is the role of the carbon and graphene chemistries importance in the lead acid batteries and advanced technology for better performance. But there is improvement or the scope for any battery technologies. Those things we can see. We have to identify a right material, right process, right engineering concept, so that we can make a device which is capable, reliable, and safety kind of things. Now the grand challenge, some of the challenges are taken here. That is today is we are seriously concerned about the health. And apart from this, actually, slide has made not with the corona, but in general. If you take some of the most prominent global challenges today are the education, socio-economical, environmental, democracy, remote control wars, and political conflicts between the regions, and poverty, and of course the energy. Energy wise, is energy demands. It is the two ways. One is the growing population, and also growing individual income as well, nation income as well. So once we have an income, naturally you are purchasing several of home appliances. That is, it may be greaser or the grinder or some anything else. So that's the consumption of energy in each and every household is continuously increases. That's why always is a supply for energy and demand is always mismatches. Hope you can. So there are several energy storage technologies, not only the electrochemical storage technologies, it comes under battery, but there is a mechanical pumped hydro, compressed air, flywheels. These are also pumped hydro. If you see that earlier installation, all are the percentage 98 plus. So the compressed air and flywheels, some of the things now people are preferring. And electrochemical, you see the secondary batteries, lead acid, nickel cadmium, nickel metal hydrates, lithium, sodium, sulfur, and sodium ion batteries, and metal air batteries, and several other kind of things. Recently, the flow batteries also it's added, and chemical, of course, this is a hydrogen based. There's a fuel cell, PMFC, DMFC, all kind of things. But today we restricted about the electrochemical, that is the secondary batteries for the lead acid. Of course, the electrical, that is double layer capacitor, superconducting magnetic coils, that's thermal energy. All these things are a bit expensive, but the double layer capacitor can be a potential candidate for the competent to the batteries, and or it is a supplement to the battery, and this electrochemical double layer capacitor can be coupled, and it be a hybrid system. It is much more effective and cycle in terms of cost, in terms of cycle life, in terms of reliability as well. So now you can see that which technology can be used, what is the typical power can be, the technology can be designed, and which can be delivered, how much is energy can be delivered, how much hour can be delivered, all these things. We can see the batteries, it is 1 to 8 hours, but it can depend on the kilowatt hour. Now this all the parallel series combinations, you can do that, and you can have even 24 hours, you can do that. Similarly, flywheel, pumped hydro, you can see 12 hours, and compressed air is 20 hours, and sodium sulfur 1 hour. So superconducting magnetic energy storage is there is 30 minutes. Capacitors, it is more related power, as you all know that. Flow batteries is again 10 hours. Similarly, hydrogen storage is more than 5 hours something. So these are the potential. You can choose that the device as per your application requirement, because commonly today we cannot use all the single battery technology or single electrochemical device to all applications. That's what I want to communicate from that message slide. You can see it is exclusively for electrochemical applications, that is the batteries. At top you can see flow batteries, zinc based, and new chemistries are coming up, sodium sulfur, and advanced lead acid batteries, that is competing with many other systems, that is lithium ion. You can see the advanced lead acid batteries is above the lithium ion batteries. People talk about lithium ion battery, but still it is but it's the cost also we have to be considered. Nickel metal hydrates, of course, nickel metal hydrate, nickel cadmium. Nickel cadmium is almost obsoleted because of this cadmium is very toxic, and you need to have your own recycling system. But nickel metal hydrate batteries that is really safe, and it's good technologies, but unfortunately the cell voltage and memory power, that is 1.2 as compared to lithium 3.6. So 3 cells is equivalent to 1 cell of lithium. Lithium is much cheaper than the nickel metal hydrates. But earlier, if you see all our toys and everything, nickel metal hydrates they used for safety purpose. But today, lithium ion is occupied the both nickel metal hydrate, nickel cadmium markets share. So high power flywheel, of course, these are mechanical and superconducting kind of things. So we can talk about only the lead acid batteries today, the importance of lead acid batteries. You can see the market till even 2025 also see lead acid battery is dominating here. You can see the green is a till that is a market report says that 2025 also lead acid battery dominates. And you can see compared to the other technology, it's very nominal as the lithium ion is picking up because of this electric vehicle booming. So otherwise, this lead acid battery, though it is a heavy density and it is a energy density is low, relatively low as compared to the lithium ion batteries, and of course nickel metal hydride batteries, and also charging is it is a little bit lower than any other technologies. So now you can see that there is a the emerging earlier we only use for the lead battery for SLI application or the backup for solar application. But today, whatever the power people are using outside, even the home electricity or the colleges, schools can be, hospitals can have their own energy storage systems. So when power is, because why is power people talk? Because grid also is a century-old grids, and it is also very highly unreliable. So that's why you can choose the demand for the battery. It comes for both home electricity, hospitals, and college, even the institutions, power grids, and also the underwater applications. Of course, the automobile for the electric mobility in future. So this power electrons, because once you have other than the lead acid batteries, you need to have a very strong power electronics, that is hardware system to control these batteries, whether it's in terms of voltage, in terms of charge, all these things very sensitive. It's not like a lead acid batteries. So that's why when you want to connect, you want to back up for the renewables, or you want to have XEVs, that is any hybrid power systems, or the electric vehicle, two-wheeler, three-wheeler, e-rickshaw, etc. But you need to have a power electronics. So each and of course, each and every technology has its own advantage and disadvantage. That's what in the previous slide also I mentioned. All the single chemistry, single chemistry, single battery cannot serve for our purpose. We have to choose the battery. We have to choose as per requirement our application. Today we are monitoring the temperature, which we cannot use a lead acid or any other. Either you have to use nickel metal hydrates, or you have to use a portable lithium-ion batteries. So that's kind of you have to choose it. So these are all the potential batteries. Only I have put here the pros and cons. And flow batteries, still it's a really good technology emerging, but unfortunately it is a lower energy density and also at operating temperature limitations. Sodium ion battery more economical, but still if you take the sodium sulfur, it is high temperature. Sodium ion is of course is now under development. Metal air batteries, zinc air and aluminum air. Apart from that, I not mentioned here. I think morning you had a talk with Professor Murugan Ramaswamy based on the metal air batteries, which is really good, but only thing is it has its own challenges we need to overcome. It is actually the COVID, though it is aggressive in second wave, it's really helping for the academic institution to learn to develop a prototypes at the laboratory itself in spite of COVID stringent conditions. And it is a great opportunity for us to develop either the solid state batteries or the sodium ion batteries or the metal air batteries at lab, which all are very not so complex. We can make it as a laboratory prototype. Once you develop and you try to have a IP on it, and definitely the industry will come to you, and then the industry will scale up. And we are also doing the same way with collaboration with academic institutions. And you can see these are the some of the things. And performance, what today we requirement is the a very good performance, very reliability, cycle life, safety, economical, of course environmental friendly kind of batteries. So now the emerging applications, as we mentioned, the flow batteries, sodium ion batteries, and nickel zinc is zinc, though it has a zinc also has its own challenges, but it is a very the performance is as good as the lithium ion batteries. Of course, metal air batteries is under development. I can say lithium ion and sodium ion is the solid state batteries also comes under this category. That's why I have not specifically mentioned here. And maybe tomorrow I will talk about all this advanced battery technology for the electric vehicle applications or the ESS application. Because today I will limit to the lead acid battery, which is really it's like a Bhishma Pitama, just because when you take the lead acid wants to die, it will die, or we are allowed the battery to die. Otherwise, it's very, very reliable and safety technology as compared to any other. It is by virtue of it is 100% recyclability. And the n number of times you can do recyclability. So today, most of the industries are using 70% of recycling materials, because you get a high purity lead material because of its by virtue of its density, high density. All other lightweight density materials are floating on the top of the surface. You can bottom, you can extract that, you can run this molten high pure lead. That's why this technology survives, and lead is very, very low cost also as compared to other. Yes, lead acid battery definitely is doing a wonderful, a great job to us, society as well. It is all the starting applications for the bus and any other thing, automotive, auto two-wheeler, scooter, anything that is doing, and also deep cycle, but is inverters, motive power. Motive power, it's one of the best, because motive power you can see for the dockyards and other thing all the time. You have to move the items from one place to other places, and it is because of its bulky, you can have is a balance that motive power application is a very good business. And of course telecoms, as I mentioned, telecom also, it's all the telecom today. We have 4 to 5 lakhs towers is powered by lead acid battery, which was first imported. The technology was first imported or adopted by the proudly say Amar Raja Batteries Technologies. We are the first to brought this valve regulated lead acid batteries for the telecom and railways. Afterwards, people have adopted this technology, and we'll discuss some high rate applications. Of course, lead acid battery with different proprietary additives it does. And only thing is that PSO, partial state of charge, the SPV, solar photovoltaic, or the solar energy, to be that's today MNRE put for 72 hours autonomy. So you need to have you have to ensure that how much is energy to be stored in a battery. You have to over design the battery pack and ensure that even the solar power is not available for 72 hours because of climatic change or weather condition, and battery has to support your application. Similarly, high rate partial state, it is coming to the, now we are moving to the automotive e-mobility, and the basic version is micro and hybrid. Scorpio is a micro hybrid. It's not completely electric hybrid, but it's a basic version of that. So you can see that the bottom, there is a symbol for that. So among us all, now we are moving to the lead acid battery, how things are going. As I mentioned earlier, this bottom is very challenging, is SPV, partial state and high rate. And if you, why the lead acid battery is low energy density and low charging for characteristics. There's, you can see this all are lead. If you take this the substrate, the lead grid also lead, again density added, and over that you are pasting that active material, which is really undergo for the redox reaction. It gives that Pb and PbO2. That's also again lead. Only the other things are the PP kind of material, polypropylene, polyethylene kind of separators, which is lightweight. But everything is a lead. When you calculate the watt hour per kg is dominating here. That's why your energy density, watt hour per kg, is lower than that. That's why we are trying to do that. You replace the grid to the very thin grids, or we are going for a graphene kind of grids, or we are going plastic kind of thing, so that the lead can be reduced to a maximum extent. And of course, this the grid is made with a different lead with alloys, calcium, antimony, zinc, because lead is very soft material. You need to have give a mechanical strength. We need to add this proprietary elements. And the negative, you can see the sponge lead, because negative is pure lead we are using here. You need to have a sponge kind of characteristics. That's why we are argon you can barium sulfate, which is similar to lead sulfate, and that lignin is organic substrate, and also you have another element, that is carbon. So all these things put together, that you call a sponge lead. So so that it will be participate in the reversible chemical reaction. Of course, the positive here, you can say positive electrode is a lead dioxide, and which you can say PbO2 plus H2SO4 gives a PbSO4H2. Here also left side you can see Pb plus H2SO4 does to give the PbSO4 plus H2. So that's why it is a you can say both the sides you have a PbSO4 forms. It is, you can say, double sulfate theory, or the rechargeable battery, any kind of things you can call it. You can see that the conventional battery we are using here is a vented. So you use only the PPP separator. So what happens? It gets evaporated. When once you use it, and the water get drained out. You might have seen in the roadside. There's when you particularly tractor batteries, they used to open up and they fill the again sulfuric acid, which is dilute sulfuric acid, and also distilled water, both combined, and then they will put a rectifier to charge that one. So here water gets drained out, but whereas in the VRLA technology, it is not like that. This is what the technology we imported from the technology transfer from the GNB from USA, and it is used extensively for railways and telecom application. It is a completely sealed battery. You don't have spillage of electrolyte. Whereas in the top one vented, you can see if you change that your battery, it will be there is a possibility of spillage of. That's why in the car or scooter also always will be vertically kept. So another battery which is very developed 100 plus years, that a tubular battery, which is very expensive but very reliable, and with a very good contact area with the lead gates. That is, here you use the spines. That's why the surface area very high, and it gives a way better cycle life than any other technology. But this grid cost is a little bit expensive. That's why it is costly, but mostly used for home UPS, home inverter application, and solar backups. So this left side yellow is our two-wheeler battery we use. We are the first to adapt this that maintenance-free battery for two-wheeler segment, apart from this industrial, telecom, and railways. So there's every battery, we also have some limitations we cannot. So similarly here also, if you leave this battery in a discharged state, that whatever it has happened, PbO2 plus H2S4 gives rise to PbSO4 plus H2O. This PbSO4 is a culprit in this technology. Once this you leave this battery in a car, your vehicle is not used, or you are not recharged this battery, then what will happen? This is if you are in a discharged condition, this PbSO4 crystals with aging, and it slightly grows. Once it grows, what happens when you charge it? These large grown PbSO crystal is unable to participate or precipitate, dissociate into the chemical reaction, because as water is specific gravity is 1. So this gravity, as a sulfuric acid is not, wettability is not there. So that's why reaction is very slow, and there is a chance of your batteries gets damaged. That's why always we advise, manufacturer advise the batteries to be kept in a charged condition, even if you leave it for 2 to 3 months. So let it be fully charged, and then you don't see any kind of a sulfation, large scale sulfation crystals. Then their battery will be perform well when you want to use it. So this, as I mentioned earlier, the partial state of charge and high rate, this is for solar application, it is for electric vehicle application. The traditional lead acid battery and the chemistry what we use may not be the performance may not but is good enough to drive for the new application for ours meet the application requirement. Now we need to modify, we need to really come to the design, we need to really come to the materials, we need to really come to the charge condition, everything. So definitely these are the challenges we industry people has converted as opportunities. We work with the academics, we work with our technology partners, we also have excellent R&D centers, state of art of R&D centers to develop our own system to meet the customer requirement to delight our customers. Of course, these are the maybe you can see these are the so many components already discussed: anode PB, cathode PB, O2H, and the AGM separator used for the VRLA, PPP. These things are used for the vented, that is a low maintenance, and gel batteries are different. So all the kind of thing. You have different versions. We have the paste recipe also. We have pre-lead and lead oxide, basic sulfate, 3BS and 4BS. Each has its own advantages, disadvantages, but we have to see that. We'll come back. So generally, when you want to design a battery, any battery, not only these lead acid batteries, we need to see this left-hand side parameter. What is your application requirement? What is your vehicle requirement? If it is a two-wheeler, it is a 48-volt system. What is your current requirement? It is 20 Ah per two-wheeler is fine for the earlier two-wheelers. But today, two-wheelers, electric vehicles, it's the people are using up to very high currents. And the capacity, what is the capacity you need? What is the energy you need? How many kilometers you want to drive per day? Those things, power, you can see, even the UPS, anything you can. Here you can see right hand side, we take the input materials and calculate and based on these materials and what is 1 gram of material can deliver. Based on that, we can calculate, we can design a battery for your applications. Of course, you can see the typical, always we are not into the anything that is either any other batteries. It is very difficult to meet the theoretical capacity, which may be expected at minus 20, say, the absolute temperature rather than room temperature. Even the small temperature makes a difference in the lattice structure. So practically, you have to use a little more high materials than the required. So these are the reaction generally happens. It's already I explained that anode reaction is this one you have a minus 0.35 and cathode reaction is 1. So there's a total cell reaction is equal chemical potential of cathode minus chemical potential of anode. So this minus gets plus, you will get a 2.4 volts comfortably, 4 or 5 volts comfortably using this lead acid batteries, which is slightly higher than other nickel metal nickel, that is 1.2 alkaline batteries, I can say that. So you can see that's a typical cathode active material and negative elements made, because I am not shared with my things because it's industry always we have to have a proprietary kind of things. This I give the more example here. You can see that all the lead we paste, we prepare a electro recipe and paste it, and these are the process conditions. We have curing, which takes a lot of is all the material be converted here into the electro PbO2. If it is any free lead is there which gets oxidized during a formation here. This formation also you have two different kind of things. Earlier people do the plate formation, that is individual plates they convert into the electrochemical, then you assemble it. But today you don't have, because demand is more and time is very consuming for the formation. That's why we make the cells and directly we do this formation that is called a jar formation or tank formation. That means even after the formation also you need not have any kind of refilling the electrolyte. So that will be the same. Of course, that I mentioned here, that is a jar formation tank. In the olden days, people used to do this tank plate formation. Then they do the formation is nothing but that initial capacity, whether you are obtained or not. Then you can check the all the relevant tests. Then during the finished stage, then we'll be packing and uh, transporting. So as I mentioned earlier, these are the emerging, that is a emerging application, that is EVs and solar, and issues or challenges. We did see that this is a kind of things, and today we also have to see why the electric vehicles we are going for. What is the necessity of the electric vehicle? Yes, the electric vehicles and ESS, it's dominating all the, even the telecom towers in the remote areas are converting into the battery based system. All the diesel generators are removed and battery capacity is increased. The reason is it generates a lot of the CO2. So greenhouse gas emissions, whether it is emitted at the remote area in the telecom towers or in the solar backups or any other places, that's why we have to have reduced the greenhouse gas emissions. And transport segment and power means that is what we are getting from the coal to the electricity. There, these are the two areas which are maximum greenhouse gas emissions CO2 generates. We are the practical example we have seen in the or the capital city Delhi. So that's why there are a lot of kind of things. They are giving a very attractive incentives for the changing that ICE, that is internal combustion. What we conventional traditional vehicles are run with ICE engine. Those things are converted into the electric motor kind of thing. So you can see that is a starting version, that is start micro. There is a hybrid kind of versions. There is a micro is almost startup. You can, that is a Scorpio, Mahindra. You see this is a micro hybrid they used to write. So that means it is a stop and start. So it is like our computer, how it is going to sleep mode. How it is when you are not using it, it will go to the sleep mode. Similarly, when because we have in the cities, we have so many traffic signals. When it is a vehicle is start, you just remove your foot from clutch, automatically go to the sleep mode, and again it will. Otherwise, what happened earlier, ambassador, you see, when you stop and start, so much of gases the CO2 emits. So to avoid such kind of things, people have started from micro to and strong hybrid, then PHEV, that is a plug-in hybrid, which runs the 30 kilometers, which required a little bit high. And the hybrid, it is a very less power is required. That's why people are using both the technology. You can see the bottom, that is the lead acid battery lithium combination or nickel metal lead lithium combination. These are the potential candidates for the this right side vehicles, future vehicles, and left side you can see the very comfortable with the lead acid batteries, and also you can have a up to 15%, 10 to 15% of reduction of CO2. You can see the evolution of the batteries. There is a traditional to the advanced batteries. So if you look at that maintenance-free VRLA, which is extensively used for the telecom and railways and UPS database centers, the center one, the extreme left, which is used for the tractors and heavy trucks and of course buses. And if you see the lead acid battery right side new design which is required, which is the lead carbon bipolar, which bipolar required. So all these things are proven technology at lab scale, but still it is a cost is comparable to the lithium ion. That's why people are thinking about it. So now you can see this, there is a scope for, because as I mentioned, that is the energy density is very, very low. That way, if you go to the 25 to 30 watt-hour per kg, and you can go for bipolar, that is a bipolar substrate, is you can reduce the lead grids weight is around 40%. So then you can increase that, that is energy density of the lead acid battery up to 70. Still it is low as compared to the theoretical value, that is 169 to 171, the variation in the voltage. Similarly, lithium ion, of course, I will discuss this tomorrow sometimes. And you can see that this is my very interesting, though I was during my PhD onwards, I wanted to work on the lithium ion batteries. I'm talking about 90s. So, but still I saw this is around 96. There is a one journal I saw that's carbon nanotube is coated on the lead grids and lead powders. And you can see the battery can be charged in 45 minutes. It's amazing to see this CNT, that is a carbon nanotube. Those days, you see the carbon nanotubes are graphene, which was developed in 10, 15 years back. The cost of 1 kg of the material is $300,000. Even today, the solid state battery also $100,000. So that's why it's very, very difficult. People are unable to adapt this, even the small additive in the lead acid batteries. But today, people are extensively using both carbon nanomaterials and CNT. Even graphene. I'll show you some of the things, graphene materials. Some of the industries are already adopted, and we are also in the process of developing and validation. Of course, these are some of the things we can use carbon foam instead of that. Earlier, people are used for the defense applications, all these things. Still, you can see that's a cold cranking because this lead acid battery is good in the cold condition, -10, -18. We all this car batteries or two-wheeler battery we evaluate, we test -18. So we see the whether really it will crank or not. So those kind of things we iron discharge. This is another new technology, spiral designs. It's similar to lithium, and the adapter is very, very bit expensive, but very limited players. But it's a good technology. So that's what I told you is the carbon technology. I would like to focus more on this, and you can have once we do this one, then I'll show what we did and what. And this carbon technology, as I mentioned, there's a lead sulfate is formed on the right side, or discharge product, right, which grows. That is one of the culprit in the limiting this lead acid battery. So that's why what some of the CSIR of Australia, what they did is they removed the entire PB here and they added the carbon. So though this acts as a very powerful and powered lead acid battery, but it loses some energy because you are completely removing this lead here, which is also participate in the electrochemical reaction. Unfortunately, it is only the substitute good for the power, not for the energy. Energy is always low for lead acid batteries, but it can be used only the power where power is demand. You can use because lead carbon. You can see it is in between lead acid and nickel metal hydride. You can see comfortably 1,000 cycles. And it is a really good technology. But unfortunately, it is a power application. To compensate this power, to balance this power as well as energy, and the people are you adopted new technology. You see, this is a very conventional one. Lead acid battery, what we are using here. Here, that the ultra capacitor people remove that negative plate. There's a lead, so that there's remove the sulfation issue, which is long lasting thousands. If it is, this gives a 0.5, this will give 1. So that means it's a 1,500 cycle, this 1,000 cycle. When to balance this energy and power, they splitted this carbon into 2 electrodes. One is original lead electrode, another one is a carbon electrode. So it partially meets the requirement. You can see the conventional lead acid, the cycle life is only the 40,000. It is used for the hybrid vehicles. It's called a pulse charge discharge. That's why it is 2 lakhs also given here. Because every time, as I mentioned, when you remove this clutch from your foot from clutch, that's called one cycle kind of, because if you have the regenerative, that will be charged to your battery. So that's why the pulse charging, you can see it is around 40,000. But whereas in ultra battery, this one is gives more than that. So this will meet that hybrid, micro hybrid, up to the mild hybrid electric vehicles comfortably with cost effective. And of course, anything we need a safety, performance, cycle ability, and the sustainability. That's much more important. That's why sustainability, if you don't have sustainability, it is very, very difficult to satisfy customers. So price is always advantage. And lead acid battery, these are all are good except the charging, and the charging also we can balance it with using the carbon and other grid technologies. Now this is, see, that's a negative, as I mentioned, it is a very sulfation problem. We also use different carbon materials, and we have done some kind of analysis. You can see we got the crystallites around nanometer size, and this I will show you the. And similarly, this is we directly use the kinetic Honda. This is a 5H 12 volts battery. You adapted that one. You can see this capacity is really good. These are the different. And here, that is the difference between the academic and the industry. We have to comply these standards. So there is various parameters to be tested. and these batteries are performing well. You can see different carbons grades, and this is HR high rate recharge. What you have to do is 10 degrees centigrade we have to do, and this is a 5 amps we have to apply for 8 times. 5 into 8, so 40 amperes. So the requirement is it has to hold the 1.5 minutes, and battery voltage should not drop 6 volts. So this can be HRD. Once you make this performance is you can have a 5 cranks or 6 cranks can be done. So your batteries, that's why even if you do 5 cranks, it is within 90 minutes you can do comfort. That's why we do. You can see the B1 battery is more comfortable. All the batteries are made comfortably meeting the Japan industrial standard, G standard. Similarly, the charge acceptance. Here also you have to see, you have to charge with different, generally we do with C, but you have to discharge the battery into 50%, not 100% charge. And your current is around 0.5. This voltage should not drop for 0.5. It is a 10 series. So here also you can see the charge acceptance is increased by 150% as compared. 100 is your required, but charge with the addition of different battery the carbon materials with having a 72 to 2000 meters per kg. That's a surface area kind of. So rate capability, generally 5H battery rate capability around 60% only. But if you have the carbon, you can see 5 to 6 we got. That is electrochemical AICTE has done. I'll explain why it has happened. Here also our requirement is only the 9 cycles, but you can see this is a one cycle consists of 480 cycles. One unit consists of. These are number of units. Unit as per the standard 9 units, but it is close to that coming up. And whereas the carbon material, the different grades, activated carbon, you see that even the 10th unit also very comfortable. That's why each unit is 480 cycles. Here I mentioned here all the HRD and other. Sometimes what happens, even the carbon nanotubes, you can see high rate is not good. These are all we published earlier, our team, some of the team members. This is what happened here. So here, as I mentioned, the carbon particles surrounded in between the PbSO4. And this PbSO4 will not allow to grow further. So during the discharge, what is the size of the particle it will be retained? Or this the smaller carbon particles will be surrounded, it creates an electrical path. When you charge it, this conducting path will be allow that lead sulfate to dissolve into the and then re-participate in the chemical reaction. That's why these carbon materials are very effective in improving the charge acceptance and also the cycle life, not only in the ambient condition but also in partial state as well as high rate partial state of charge. Yeah, this is what people are using for the carbon particle. As we have seen this, you look at this graph. Here the carbon particle, these are the whites are the PbSO4. But whereas if you use a graphene material, here sometimes you may lose the contacts between the lead sulfate to this carbon. You may not have a good, sometimes these neighboring lead sulfates may grow faster. But if you have the graphene sheets, if you are able to develop and your internal resistance of the battery is significantly reduced, the mechanism has reported here. This is American Chemical Society, ACS Omega. And generally what happens, you can see the performance. It is a control sample, is a 40 volts and 20 ampere hour and 100% DOD, depth of discharge. And you can see this is beautifully charge cycle life. It's a lab scale, that's why cycle number is low. But otherwise also it's a proven kind of thing. And when you have the carbon or when you have the graphene, what happens? This water loss is happening generally. So this water loss is always will be linked to the life of the battery. And if it is a water loss rate is high, naturally what happens? This BRLA battery in particularly, your sealed maintenance, you cannot do it in a roadside like how tractor batteries are removed and refilled with dilute sulfuric acid with this distilled water and again recharge for the rectifier. That cannot be done here because it is completely sealed battery. That's why water loss also. It's a beautiful results they presented. This one I picked up only couple of results and the graphene. But graphene you have to see how you can make a graphene single layer some layers and which definitely give the very good performance in the lead acid battery too. And my dream also it's someone is really wants to work on this. Unfortunately, Indian people except Karaikudi CSR laboratory, no one is working on that. We can see the some of the results also what we have done at the lab scale. We are extremely 20% is improved as compared to the control samples. This is what we did with the different graphene in the lab scale, but it's yet to is a 3 ampere hour we did, and it is yet to do a lot of research as to do before it goes to the commercialization side. Of course, this is what I mentioned is PB2 plus ions will effectively participate sufficiently available for charge process. We are conducting path around lead sulfates, then the better kind of. Yeah, that's these lead acid batteries. People talk only not necessarily the lithium acid batteries are used for electric vehicle. Lead acid batteries also used for the electric vehicle. If you see the Reva, even car, even till last year they used lead acid batteries very comfortably. And today, of course, lithium ion is around people are adopting, and its cost is less. So you can see that how much emissions are happened. And India is also because of huge automotive sales or that industrial kind of thing, we emit so much of CO2. And that you can see that electric auto e-rickshaws very comfortable, and I can say it is the best business not only for the e-rickshaw owners as well as the battery. It is North India. You can see the Delhi, Chandigarh, and Lucknow, many areas, Haryana, all even Calcutta and all UP. Many areas e-rickshaws are dominating, and they are also. It is a three-way advantage for the owner. Is pedaling is not there, and you can drive for the number of kilometers. You can add more. Similarly, electric vehicle, that is a car is yet to come because the cost of the battery and lead acid cannot be used because of the charging system. People are talking about fast charging, and of course golf carts and this municipal waste. People are working on that, and many municipalities they are adapted the e-rickshaws and e-tempos to collect the wastage and all. So that is these are the e-rickshaw, e-auto, e-tempos, and the two-wheelers are the best business. Can be used this advanced lead acid batteries for that. So this again, this what you need is partial state, and think we can see some of the things. This is what I mentioned because this graph supposed to be kept in the electric vehicle. So you can see mild mileage how much is there. People are working on this later on, moving later on going to the electric vehicles. So this you can see when you have fuel efficiency as well as CO2 efficiency when you move from left to right. Okay, that's what I want to show. Here you have a pure electric vehicle. You will have a high CO2 reduction, high efficiency of fuel. We also done a lot of work on the both paste recipe and this different kind of batteries, and we also got some kind of improvements we are working on. We also new technology initiatives, as I mentioned. We are also using high rate capability kind of the new technology which is imported technology transfer from USA. That is a 60% more durables and 70% better electric flow than the conventional. It will be 20% greenhouse will be less. It is not necessarily when you do it outside recycling or process. In in-house manufacturing also, we are trying to adopt new technology, new improve processes to reduce the usage of consumption of energy as well as the improvement in the performance. Similarly, we also recently got a license of the potential bipolarity. As I mentioned, bipolar, you can see here the bipolar advantage of if you have a bipolar, good bipolar, one side you have positive, another side you have negative, but all the flow will be vertical. Here is the horizontal. If you have plate, again charge, discharge, all electrons will go and completely down and get converted. This material again draw the currents here. But whereas this one is very comfortable, you can see that the 40% can be less lead weight weight can be used, because 50% is almost reduced here. This bipolar substrate also not made with the lead. It is made with a different zirconia titan kind of composite material, and that's why you have this technology now. Last year we have got a license. We are now adopting this technology, and our collaborators are working on this. If it is Indian countries, if it really works, and all our traditional thing can be migrated to, at least 50% can be migrated to this technology. We can reduce 50% usage of lead, and of course, you can see all our batteries. We are industrial batteries. We do it. This Taj Mahal also powered is 2,500 Ah, the VRLA batteries, and we can see the hydropower. And also our second location located in the Chittoor, that is new plants, all are solar powered. And we also see the VHL and offshore kind of things. All our latest industrial batteries are used for. This is telecom also. So used for this one. Even telecom people, they removed the diesel generators. They added this battery. Earlier, the diesel generator works 16 hours, 8 hours battery or the grid line. Now 16 hours battery backup and no diesel generator kind of things. And they have, to charge this battery, you have a solar, you have a wind in remote areas. Of course, we very recently our industrial batteries, we have Nigerian, we have adopted is the largest, you can say, once it is completed, complete project. It is 40 megawatt hour. So today we have completed up to the 8.5 megawatt hour kind of things, whereas you can see how much they are CO2 is saving. This is one big project we have executed very recently in the one of the university. So of course we can see the same thing. These are our earlier installations. So of course we cannot design the batteries. We can only see up to 100 years. We don't know after 100 years what kind of technology will come, geothermal, solar, or anything. Even Abdul Kalam used to say that you can put a panel on the space to get a solar power and all. So that what is our commitment, Indian commitment, we have to reduce by 33% by the 2030, 35, in between 33 to 35%. So that is all the electric vehicles, if it is ICE, that is internal combustion vehicle, convert at least 30%, we can reduce comfortably 37%. Of course, we can other that is solar is already 175 gigawatt hour by 2022, another 50 gigawatt hour per hydrogen. All these things are put together to 25. Government has announced very recently. The cabinet central government has also approved a big budget for the PLSA scheme for starting the battery advanced other than other batteries for the electric vehicle application. You see the huge requirement for the 50 gigawatt to 60 gigawatt of kinds of things. Yes, thank you very much for this. These are all I can say. The summary also is included, so I am not done. And you can take that takeaway things are that the battery can be the carbon materials are very, very effective. You have the capability. All the engineering graduates or faculties can guide the students, or the engineering graduates can bring the innovative designs. People can develop a novel materials, nanomaterials with desired properties by combination of 2 or 3 synthesis processor, or you can control the particle size during the synthesis itself. So you can you are having a control over the particle size, morphology. All these things are matter when it comes to the performance point of view. So these are the some of the things. And tomorrow for all the electric vehicles, to go to the solar charging, really there's an electric vehicle. It is a real green transportation. We can say that it really sustainable, and the charging also we need not depend on the grid, which is very unstable, and stress also more when you connect to the charging all electric vehicles at a time. That's why government is also having a promoting the solar rooftop, because each house can be a power source, each village can be there can be an energy center. You can generate your own energy, you can have your own power, but the only thing is you need to have an initial infrastructure, that is a backup system, battery backup. It may be lead acid battery or any other technologies which is commercially viable. Those things can be in a future. So you can more effectively we are tapping up the solar energy requirements. Thank you very much for your kind attention, and I'm happy to receive some discussion.
Okay. Thank you, sir. Thank you so much for your reflective and provoking lecture. Thank you so much, sir. We are grateful for your time and talk.
You're most welcome for questions. Any questions? Any discussions?
Yes. Now the session is open for any some queries you have that on your mind. Now you can raise your hands, or else we can wind up the discussion. In case you don't have, you can raise your hands either, or you can voice out your questions.
Yeah, sir. You can ask.
Hari Prasad, sir, you can unmute your.
Okay.
No. Yes, sir. Hari Prasad.
Hello, sir. I'm audible.
Sir, your voice is dropping. Hari Prasad, sir.
Now is it clear, madam?
Yes, it is clear.
Okay.
Yes. Okay.
Somebody, sir, you are asking some question?
Yes, sir. I will ask a question, sir.
Yeah, please. You can.
Okay.
Yeah.
Are you there?
Issue here, sir. Sir, actually, I'm doing connection. So now is okay. Is it okay now?
Yes.
Yeah. It is.
Yes.
You can.
It seems to be okay now.
Yes, sir. Sir, I would like to know the role of the active carbon participation in the battery. So whether performance improved if increase the active area of the carbon material along with the lead. I mean, lead sponge. Hello.
You can open video and you can ask directly, sir.
Yes, sir. I'm asking, sir, but my device has some problem. That's why I'm just directly asking the professor, sir. I'm from
Venkateshwar, sir. Please
I'm
unmute.
Attending. Hello.
Venkateshwar, sir. Please unmute your audio. Okay, sir.
Yeah, that's see, as I mentioned, this lead acid battery, what happens, that is both are the electrodes are lead and PbO plus H2SO2 PbSO4. So this PbSO4, what happens, even the small temperature variation, it tries to grow further.
Okay,
once it grows further, and when you are recharging it, what happens, that is H2SO4. There the end other product is water. So water is not exactly 1.0 specific gravity. It is 1.1, 1.2. Something is immediately available. So reaction will be sustained. So otherwise, what happens when you charge the battery? These all the carbon particles will be surrounded the lead sulfate, and effectively dissolutions will happen, or that means this sulfate will be reconverted into the participated into the Pb and PbO2. So this 100% this reaction is sustainable. Then you don't see any degradation. The carbon particles are always will support, or the one is create a conducting path. One is to will not allow to grow PbSO particles to large enough. So all the Pb particles will reaction. Only thing is the carbon particles some of the water is losses occurred, and these losses can be minimized with various other additives or the design itself. That's why in the graphic case I have shown the water losses,
Yeah,
and
yeah.
earlier some people are water loss, but the that is today graphene material is a wonderful wonder materials, and you can even it is you can apply in any stages, process stages also, to ensure that your particle size will not have your internal resistance of battery will not grow, and once internal resistance is not there, your the performance is sustained, your cycle life is sustained, you can comfortably meet the design life, your customer will be happy, you will be happy. So that's the kind of.
Yes, sir.
Am I?
Thank you, sir. Yeah,
Yeah.
yes, sir. Actually, so then the lead acid, no. So how it compete with the lithium ion battery as the no, this comparatively lower than the lithium ion battery, sir? What are the effective strategies would help to improve the power output,
Yeah.
sir?
Yeah. As I mentioned, that is as lead sulfate is one of the culprit.
Yeah,
Okay.
PV
Another
so
it is that weight. Lead grid we are using, that is another weight. So weight, if you reduce the weight, suppose you put the same lead on the plastic grids, or you, as I mentioned, the bipolar plate. So if you reduce the grid and the specific energy density, that is equal watt hour per kg. Kg your battery weight, that is battery total weight, which you are
yeah.
reducing. So that energy density automatically will improve, and that carbon particles automatically improve. Today, what we need is, I am not going to compare the performance with the lithium ion,
Lithium
but
ion.
what I'm saying is, if your lead acid battery is quick enough to recharge, because conventional lead acid battery takes 8 to 10 hours. But when you have a carbon or new design kind of thing, you can get it as a 3 to 4 hours, and e-rickshaw person or e-auto person or two-wheelers, where
Mm.
the weight and that is a space is not a constant, and you get a very low cost of these batteries, and these batteries are good enough to serve the purpose of this segment. I'm talking low end segment, two-wheeler, three-wheeler, e-rickshaw. So
Okay.
I'm not saying that yeah, the car and all, because high end people, though they may be affordable to have, or because if are the large scale Ola, they can use it. But if you use the carbon particles, see that what is the charge acceptance time. Whether it's
Mm.
reduced, yes, good. If it is not done, then something you need to do. So that's why if you have that's what the carbon nanotubes, when they put it on the lead grid, lead materials, that what I read in that hypothetical
Mm.
news appeared in the magazine in '96, I remember,
Okay.
billion times of surface area increased.
Yes. Mm.
So that made that the charge acceptance time is less than 1 hour.
Yeah.
But today I'm not sure whether we can reach to that level. I am a very practical person.
Practically, it
If
is.
it is
Yeah.
a
Yeah.
2 hours, 3 hours is good enough for the two-wheeler person, right? E-rickshaw
Okay.
person. If it is
Mm.
because if you are coming at 11 o'clock you put for charging 3, 4 hours or 6 hours. Morning 6 o'clock you want to go back. That is 11 to 5, 6, 7 hours is comfortable to
Comfortable. Yes.
charge your
Mm.
fully battery. If you are
Correct.
not charging fully, what happens? You cannot cover the mileage, then
Mm.
somewhere it will be stuck. Your customer will be uncomfortable with your e-rickshaw owner, right? So a
Yeah.
lot of misunderstanding, a lot of confusion happens. So you have to ensure that your battery, whether it's a lead acid or lithium, whether it's 100% is charged or not. If it is 100% is not charged, at least lunchtime or during some one trip, you have to put for charging 85% or 90%, then the battery can be used. If you are
Mm.
not, if you are leaving, I mentioned it's sometimes if it is fully discharged, what happen? You don't have specific gravity. The water is very low. When you want to charge it, it is very difficult. What you have to go, you have to apply very small current. 20 hours rated. So this 20 hours again taking a time. So that you don't have time, no, right? You are a day-to-day wage person. You unless otherwise you pedal it, you drive this e-rickshaw. It is very difficult to earn the money. So is the daily wage basis that you have to ensure that battery has to be 100% full state of charge, so that you can cover your mileage, you can earn your earnings. That's what that's the way I'm comparing. And
Yes.
these three segments: e-rickshaw, e-auto, and this municipal waste. All these two-wheeler, you don't need a space constraint, right? You don't need
Yeah.
a smartness also, because car and other buses are that is different cases, and that you need altogether different infrastructure for the charge, different power electronics charge, different hardware system, because there the thousands of cells are connected in series parallel kind of system. So those things are different, and you can segregate, you can classify the segment, which segment you can use a latest battery, which
Yeah.
segment you can use other batteries. Segment.
Based on
That's why.
demand. Yes.
Yeah. Please.
Yeah.
Am I answered?
Yeah. Yes, sir. Yes, sir. Thank you, sir. Thank you very
Please.
much, sir.
So any other queries, participants? You can raise your queries. Or else we can.
If you are not asking, I'll ask more questions.
Yes, sir. That
How many
is.
faculty member, ma'am? How many students attended? How many faculty members?
Mostly it is reached for 120, sir, totally.
No. That attendance.
How many teachers?
Faculty ratio.
How many of them are teachers and how many of them are
Teachers,
students?
I would like to. I don't know whether if you are not taking other way.
Within this section,
I used to advise you don't need to do just take one good paper, read out, and give to the BTech or MTech students who are working with you as a project. That with that knowledge, you can have a small publication. You get a confidence. You can slowly build up your own laboratory. See, it's not that someone has to do or some all the time. You can see today people are in corona, they're developing their own kind of mask, or keeping the kind of things, or the oxygen kind of so many things you do your own, right? Our kitchen also you have your own. So here what I suggest to today, the students are very brilliant students, they are very knowledgeable people. So how we are going to tap this solar energy? We get a lot of solar energy, but how we are going to tap? Where how to intelligent way you have to think, intelligent way you have to design your device to store more energy. Similarly, you try to extract, you try to see that see, I'm not saying all the 60 students in the class will be excellent, but at least 10 students will listen to you, 10 students will be definitely will be contribute to the their contribution, their innovation, their way of thinking is different. Those ideas will be definitely will be a futurist, will support or contribute to future requirements. That's what I wanted to advise to the some of the faculties who are interested in research, are interested in guiding the student in to the students in line with the society requirements, coupling to the society needs. So today, what that we just guide them to give a degree, and those people will write a or look for job, higher studies, or here and there and all. But that even the BTech projects really, some of the students have done extremely good because I used to earlier used to guide all the BTech students, and that is what some projects they used to come for 3 months or 1 to 3 months, and I used to give that how you can design a small instruments. These are temperature controllers, kind of things. So how to calibrate all these small things. Really, they do that. They develop a good software using MATLAB, or they can even work on any other materials. That's why. So all our teachers, because people who are here, you are the, because if I say they will not listen, but you as a teacher you say they will listen to. Because I have seen in the children's also, they will never listen to us. Whatever their teacher says, that is only final. That's why, as a teacher, if you take some good tap the some good students, who you can give some. You read one good paper because there are thousands and hundreds of papers are coming in the literature. It's publishing online. It's most of the things are available in open access also, including ACS is also available. But what I showed a graph in, it is available in ACS, Omega kind of thing. So some even RSA, ECS nowadays many things are coming up. So otherwise also people can get in different sources. So I would request all the people, see, don't worry about the whether you are working in a highly graded premier or non-premier. All are today equal. There's the knowledge is not the shareable. It has to be created. Okay, that's earlier people used to say infra has to be created. That's why many private institutions created infra and then added the faculties, good faculty with. Today it's the same thing. You have enough literature. When we are doing a PhD, I have to send a paper through the C-mail. That C-mail also I have to wait for the government post stamps. So coming and going, it takes months and months. Yearly one publication is hardly we get. But you people are even my colleagues who are working on this field, they are really put efforts within their PhD period. They published 25 papers within 3 or 4 years in excellent journals. That is all international crystallography journal. It is very, very difficult. I myself is surprised how my colleagues have published. When I was working as one of the engineering college in Chennai. Okay, so please look into that. What are the possible concept only you take it, not necessarily difficult concept you don't take it. You take it a smart concept. Smart means measurable, recordable kind of things. Those things only just very simple onwards you start it, and definitely you will be one day you will be the expertise in your field. You can definitely come out with a innovative device or innovative material can be given to the industry or society, some kind of tools. Yes, please. So with this, if you have any more questions, you can even tomorrow also you can ask more and more questions. No problem. That will be more. If you are not asking, I will ask more questions because you people already acquired a knowledge on all the batteries, right? I heard through Dr. Hari. So our colleague Balaji Rao has covered the sodium-ion batteries, which is emerging. You can all can take up, not only the Balaji Rao. That is the Dr. Murugan Ramaswamy has covered, I think, morning metal air batteries, lithium air, silver, this aluminum air, which is already people, some startup people are using. I don't know how, I think definitely my friend would have covered all the things. So there's a lot of scope for the teachers. Lot of it. That does not mean that you have to do, so you have to get some project. Not necessary. Pardon? Pardon?
Anyone? Somebody is asking question.
Yeah, please go ahead.
Anyone is there?
So if you are tomorrow, you are not asking, I'll ask more questions.
Come to the photo section once.
You can switch on your cameras.
Just we will go to photo section. Everyone open your start video, then we can able to take the photo section.
Video is not start because host is not allowed that videos.
Fine. Anything?
Okay.
So don't think about that your background or something else. That's whatever you are, you're different, but you can start new normal. Okay, you will enter into the new normal. How we enter into the because of COVID pandemic new normal. So a lot of things we are taking protection for our life, for our loved ones, and all these things. So similarly, you also can because my experience I'm sharing. It is not that I don't know whether you'll. And my own colleague that is who did a master with me is just MTech, but he has got 23 patents, and now he's guiding, he's directing the industries in USA. So the all the time when he comes here and what fellow you people are doing this, I want a battery for to run for 24 hours because he's a director level. After the one company he got 25 million dollars it seems. So that's why everyone has you can. It is easy. I think Dr. Hari also has some patent. It's easy to adopt that kind of even the small or big. You can go for a design patent. You can go is a text patent. You can go later on. In future it will be useful for you. You can when you go to the industry. You can that your patents, your designs will talk. Okay. So all are absorbed this new technologies.
Yes, sir.
Sir, we need to make it for all our, we kept for mute all the participants. So they cannot, until they
Actually,
are,
we muted the participants,
we muted all.
unless, until and
No,
unless
no,
they
that's
want
okay.
to.
But participants are listening now. So at least see,
Yes, they are listening.
see that's all are excellent speakers. See, I can say the Dr. Hari has selected excellent because we are not known to the world, but we are the first people first started this solid electrolytes in our laboratory, and our Indian solid state father of Indian solid state, Professor Suraj Chandra, where I graduated, he was my teacher. And one of his daughter is my classmate. She is working as a professor in Delhi University, and son is working as a faculty professor in IIT Kharagpur. So he was a very smart guy. He used to explain, and that Pondicherry is also university is also one of the pioneered in solid electrolyte solid state batteries. So where Ari got a doctorate degree, and all the teachers. Ramaswamy Murugan is also is my colleague. We both are classmates. And Balaji Rao also he was looking for kind of thing. So all are advanced. Even the Martha is also developing all kind of. We don't know tomorrow which technologies really work for them. Okay, that's why your invention definitely will contribute to the society for the benefit, or you have to think for the benefit of the society. Once you think like that, you will not only helping you and your family but also to society. Then effectively we can eliminate reduce this carbonization into we will transform our carbonization society into decarbonization. We will provide a clean air, and then we'll also protect our environment. We are also protect our soil, water, air, everything. Will give a better aid to our senior citizens or family members or society. Thank you very much for your kind attention. So if you have any question, please tomorrow session you can we'll have a continuation, because what we have information is huge information is available in the Google search engines and all these things. But only thing is you clarify your doubt, you clarify your concept with discussions, and then definitely that will have added advantage to your or you can build your own research group. Yeah, so thank you very much. You can always interact with me anytime. So I am always will be available for all the this battery related technology, not any other things. So this if you have any kind of, so because we as an industry try to always support for the academic institutions, and to be just tomorrow I'll get time or not, because it is a huge topic of the lithium ion. So much application I have to cover. And see, I have association with all IAC, that is the IGST, that Indo-German project. I was also one of the collaborator. The imprint, I was also one of the collaborator with IIT Kharagpur with all the spinel batteries of the lithium ion. So we also have a Roorkee, that is sodium ion batteries. People are working. Maybe that you know this Professor Yogesh Sharma. He already developed some kind of sodium ion battery, and is a many people, even IITs, where people are developing ICEs, and you are also one of them. You consider it as okay. So that is a collaboration. We are the first to establishing a joint research center on the battery technologies, various battery at SRM University in AP. So that center will be effectively operated in 21. It will be inaugurated. So already we are a huge amount we are spending on that, and they are also. But the only thing is, I suggest you should have a good internal collaboration. That is a interdepartmental collaboration with the chemistry, physics, mechanical kind of things. When you want to have a electric vehicle system, you wanted to work on the electric vehicle system. It is not the one department, one expert can do. You need to have a IoT based, you need to have a thermal management for a mechanical person, you need to have a hardware system BMS that has to be developed by that is a triple people, chemistry people can material can done, physics people can see the what is the intercalation mechanism, how to do that extract, and other engineering people can see the smart engineering can how the interfacial resistance between electrode and electrolyte can be reduced. All these things can be done, and with our sincere efforts and your efforts, then definitely we can do that. Okay. Fine.
Thank you.
And,
Thank you, sir.
I think so. We are close to the time. 3.224. Yeah. Fine.
Yes. Thank you for your great inputs and abundant suggestions, sir.
Most welcome, ma'am.
Thank you.
I can sign off.
Yes, sir. Please, please.
Thank you all. Thank you all once again for your kind attention.
Thanks to all the dear participants for attending and for being attentive till the end. So for tomorrow, we will plan for another 3 sessions, and kindly keep the same pace as you have kept today. Thank you so much.
Thank you. Thank you very much.